I invite Professor Jayant Murthy to take over the stage. Jayant?
Okay, thank you, Ishwar. Let me see if I can share my screen again. Just because I did it once doesn't mean it will work again.
Yeah, one minute.
Okay.
I'll check the audio along in the YouTube.
Sure.
Yeah, thank you.
Yeah, we still have a few minutes, which is good.
Don't know how I can get rid of this thing on the top.
Oh,
The
you are.
Zoom hide video panel, is that it? Hide floating meeting controls, maybe that's it. I have two screens, but somehow I can't move it. Oh, anyway.
Maybe Prasanna can guide you, perhaps.
This worked.
Are you there?
Okay, this worked.
Okay.
Tell me when I should start.
Yeah, Crispin will
Sure.
go ahead.
So Prabha, the lectures are 1 hour 20 minutes. So that is definitely some time for questions. 1 hour 20 minutes, right?
Yeah.
Yeah. Okay. So you have some lecture time and then question time as well.
Yeah. So maybe this is a good time to mention that.
Yeah.
So so we don't have a fixed format that people cannot ask questions during the lectures. People can, so they have been given instructions to, they can type the questions in the chat box and the chair will read it out. So for the first session for Jane's talk, I will be reading out the questions as and when the questions come, because Jane prefers that the questions are asked in between the lecture. So he can go on till 1 hour 20 minutes. I would request Jen to leave about 5 minutes at the end so that we can take questions from YouTube.
Yeah, sure.
Yeah. So apart from that, if there are questions, I'll read it out from for the Zoom people. I'll read out the questions. I'll interrupt you.
And you probably will give instructions regarding hands-on sessions before the hands-on session itself, right?
Yes, there are some set instructions which I'm going to send by email.
Okay.
I was going to put it on the IIA website, but the IIA website is not accessible from outside till now. So I could not do that.
No, it is accessible.
From IIA it is. In the morning.
No, outside. No, okay.
From my home.
You can also do one thing. You can start a Google Doc Google Doc,
yeah,
and share that with all the participants. Just to send them email and let them keep watching that page for updates.
Mm-hmm.
Yes, you can avoid sending emails. People have to just watch that page for updates.
Yeah, we'll do that. So for today, there are no particular instructions. Okay. For tomorrow, there are. So, yeah, by maybe around lunchtime, I will send it out.
I think probably you can start. It's
yeah, I think you can start. I changed the link, but anyway, it is in the playlist. If people are noticed, they can join it. I inform in the chat box also. Prabha?
Okay, yeah, I think Jane can start.
Okay, so as Anpurni and as Prabha said, this is a different type of session than the one we've normally had. Normally we pick about 40 students and they go to Kodaikanal. And that is a good thing because it allows people to meet and you can talk astronomy for a long time. On the other hand, the engagement with these online talks is far beyond what we've normally get. Instead of 40 students, maybe we have 400 students or even more. And this has been true of all the talks. Just the engagement is so much more. So in future, what the best way to proceed might be, who knows? And I might say that this is something that we're thinking about in astronomy as a general, even for professional astronomers. It is now possible for us to attend meetings all over the world, whereas before we would have to struggle for 6 months with visas and flights and all of this silly stuff. Now it's easy for us to just connect through Zoom or WebEx or whatever it is. So as this pandemic, it has offered us a chance to relook at the way we've done things. Now, the second thing I wanted to say is that Prabha asked me to give a talk on astronomy and instrumentation. And astronomy is a huge field with, yeah, I'm sorry, could everyone mute themselves who's not, unless they have a question? Okay. If you have questions, please ask them in the chat box, and then the organizers will read them, because when we have so many people, it gets disruptive if everyone talks at the same time. Okay, so as I was saying, astronomy is a huge field, both the science and the instrumentation. And so when Prabha asked me to give a talk, I deliberately didn't ask for more instructions, because that starts to be too constraining. So what I chose to do is to give an overview of astronomy from the beginning, when it started. And I'll go through the history, because I find the history of how things developed to be fascinating. And I'll come up to the modern era. Now, I have more or less 1 hour, but as I said, please feel plenty of time for questions. Not a hurried talk at all. So please do feel free to ask questions whenever you want. Now, astronomy is really the first science. And without astronomy, we wouldn't have had civilization. Civilization is living in cities. You can't live in cities unless you have farming communities, agriculture, settled areas where people come together. And that all depends on astronomy. It depends, you know when to plant by looking at what stars are in the sky. You know when the floods are coming. Again, you look and see this star rises. The sun is in this constellation. And so this is what drives your yearly schedule, how you know what to do at that time of year. So this is how astronomy began. It began by noticing these correlations. You look up at the sky and you know that it's going to get cold. You look up at the sky and you know that the rainy season is going to start. And so from there, it's an easy stretch to say that, okay, well, if we look up at the sky and the stars come at this time of year every day, well, maybe or every year, maybe it's because the stars come there that we have to do this. So you change from observations, from seeing that the sky looks this way when you do something, to predictions. So now you look at the sky and you say, okay, well, this happened, and so that governs our daily lives. And so for millennia, there was really no difference between astrology and astronomy, in the same way that there was no difference between alchemy and chemistry. So what is astrology? What is astronomy? Astrology is basically, at least in the modern era, it's basically nonsense. People look up at the sky and they pretend as though the position of the stars, you can look up and say, oh, Mars is in Aries today. I mean, I don't know if it is, but they say Mars is in Aries. And because Mars is in Aries, it's a good time for me to take a bath, whatever it is. And you get this in newspapers. You can send an SMS and 20 million other people will look in the newspaper and send an SMS, and presumably they'll all have the same day. So astrology is nonsense. There's no, the universe doesn't care about us. We're here, universe is here, and the universe continues on regardless of what we do. It doesn't even notice us. So that's astrology. Now, astronomy is the observation of the sky, observations of stars, as I do, observations of the interstellar medium, the stuff that's been between stars, observations of galaxies. Astrophysics is the study of the mechanisms in those objects. So if I look at a star and say, this star is blue, why is this star blue? It's blue because it's hot. Why is it hot? It's because it's big and it has it produces a lot more heat in its core. These days, astronomy and astrophysics basically mean the same thing. There's no difference. We all study the sky. We all try to understand what we're seeing. And in many ways, astronomy is different from many other fields. Because if I'm doing a biology experiment, I can look at my fruit flies, and then tomorrow I can look at my fruit flies again. If I'm a particle physicist, I can go to my accelerator. I can do an experiment. Tomorrow I can do the same experiment. In astronomy, I'm not allowed to do experiments. And maybe that's a good thing. You don't want people changing the temperature of the sun just to see what happens. So all in all, it's probably a good thing that we can't do experiments in the sky. But it means that we're purely observational science. We depend on what we see from the sky. And this affects us in many ways. In most of science, reproduction is important. You have to do an experiment, and then you have to reproduce your data. If you can't reproduce your data, then perhaps the first time you did it, it was just some random noise, maybe a spike in the power supply. You just don't know. In astronomy, we get data, and these data are not always reproducible. And one of the fields in which this is most important is SETI, the search for extraterrestrial intelligence. Maybe an alien race has sent out one signal. We catch that signal. Maybe we can't see it again. Then what do? And this actually happened. There was the WOW signal from where they observed a radio signal from space, but they've never seen anything again. So was it real? Was it just a fluke? I mean, we just don't know. All right. So that's astronomy, astrophysics, and astrology, which we won't ever talk about again, except for this slide. So as I said, it was an easy stretch to say that because when we see the stars, they at some point in the sky, we know to do something. Easy stretch to say from there, okay, now the stars do something, and so that tells us what we have to do. So over here, let me see if I can change my pointer. Just 1 second. Screen. All right, great. So in this slide on this picture on the left, this is from an Assyrian, a Neo-Assyrian, whatever Neo-Assyrian is, king, and the astrologer. Remember, I said there's no difference between astrology and astronomy back then. He said that there was a meteor in the sky, and so because there was a meteor, the king could do some things. And the picture on the right is again, please make sure you're muted. The picture on the right is from the Bayeux Tapestry, and this is just before the Normans invaded England. So this object here is Comet Halley. And so again, 1066, it's natural to say that because we see a comet, great things are going to come. This is from Shakespeare, when beggars die, there are no comets seen. The heavens themselves blaze forth the deaths of princes, when Julius Caesar was assassinated. Astronomy was also very important for navigation. And so what this is an astrolabe. And what you do is that you look at Polaris, and of course, this only works in the Northern Hemisphere. You look at Polaris, the North Star, and the Polaris just so happens now, it wasn't so in the past, but it just so happens that now it is more or less at the North Pole. And so you take your astrolabe, you align it to Polaris, and you have this level here. You align that to the horizon. The height of Polaris in degrees is your latitude. If Polaris is at 70 degrees in the sky, that means that your latitude is about 20 degrees. So you use astronomy for telling you where you go. Now you note that this will only tell you your latitude; it won't tell you your longitude. And this was a real problem for much of human history. People knew where they were in terms of their latitude, but they didn't know their longitude. The way we do it now is we have GPS, and the GPS satellites, they tell you where you are within a meter. If you're in the military, probably within a few centimeters. And so you know exactly where you were. But until then, there was really no way to tell where along the Earth you were. And this led to some pretty major disasters. There was one case where I think it was a Spanish Armada. They set sail from the western edge of South America. They kept heading west, hoping to hit an island. They didn't hit it. Then they came back east, came back to the mainland, and then they headed west again. And then finally they did hit that island. And that's just because you didn't know where you were. There's a major competition in the 17th century to develop accurate clocks, because once you develop a clock, then if you know what time the sun rises, that tells you your longitude. So now you know the longitude and latitude. All right, so astronomy was also important for calendars. And this is something that I actually find fascinating, because I don't understand how Hindu festivals work. So most festivals, for instance, I was born on Gokulashtami, which is the day Krishna was born. And that varies between September and early August. And because the Hindu calendar is a lunar calendar, there's only, the lunar calendar doesn't quite match up with the solar calendar. And so the Hindu festivals have some range. They move throughout the calendar. I think it's every 13th year, they add an extra month to bring the lunar calendar back in sync with the solar calendar. The Muslim calendar doesn't do that. And so you'll find the Muslim festivals traveling throughout the year. So this is true of most of the Indian festivals, except for, I think it's Shivratri, which is on January 14th. Except when it's on January 15th. And so it's just some magic calculations that I don't really understand. The modern calendar that we use is the Gregorian calendar. And so this is a successor to the Julian calendar, which was introduced by Julius Caesar. Now, the reason that Julius Caesar introduced the Julian calendar, or he had his priests work up the Julian calendar, is because, again, no one knew when the festivals were. And so this was a major problem, because the priests would work out when a festival was, they would work out when to have a holiday, but they wouldn't let you know until a couple of weeks or maybe a few days before that holiday. And so there was no way you could plan for this. And so what Caesar said is, it's better if we know exactly when these holidays are. And so they worked out the Julian calendar. Now, the Julian calendar has 365 days in the year, but a solar year is not exactly 365 days. It's 365 days plus an extra quarter day. So every year you get a little bit out of sync with the real calendar. And maybe this isn't a problem, except that it was a problem for the Christian church because Easter, for whatever theological reasons, they knew that Easter was a spring holiday. It happened in April. But as the Julian calendar kept getting out of step with the solar calendar, Easter kept moving. And so they said, okay, this is not going to work. And so Pope Gregory put in the Gregorian calendar, where now you have a leap year every 4 years, except on the century years, when you have a leap year every 400 years. So 2000 was a leap year, 1900 was not a leap year. And this almost works, except that every now and then we're still a little bit off. And so every now and then they add a second or subtract a second from the calendar. And so in the pre-computer era, no one ever noticed this. It was just adding a second to every few years. Now there's a debate going on. Should we add this second or not? And I don't know what the final result would be. But finally, in about 1600 or so, we came up with the Gregorian calendar. And this was not established in the British Empire until the mid or maybe late 18th century. And so if you look at dates in the, if you look at dates in British India, for instance, you'll find an offset. They just added a month or whatever it was to say, okay, we're going from the Gregorian calendar. I mean, we're going from the Julian calendar to the Gregorian calendar. So we'll just add a month. This 1 month has disappeared from your lives. The Russians did it much later. The Russians didn't do it until the Communist Revolution. And so when you're looking at dates, you always have to be careful. Okay, so this is all ancient astronomy till calendars. Now we come on to the first of what I call the modern astronomers. Now, before, I mean, this is in many ways a generalization, but we changed from a system where people looked at the sky in order to for some practical purpose. For instance, the Chinese have an excellent record of astronomical observations dating back to the beginning of the Chinese empire, to the first Qin dynasty. And the reason they did this is because they wanted to keep track of astrological data. So they have a record of the Crab Nebula, 1066. They have a record of comets. They have a record of meteors. And people have gone through the Chinese historical archives, and they've done this historical astronomy. They've gone and seen what happened at various dates. Unfortunately, for whatever reason, we don't have that in India. We don't have a very good written record for the last, excuse me, for the last few thousand years. But sometime around the Renaissance, now people started looking at science as a way to learn more about the universe, just as a means of learning. And when you look at a modern scientist, this is what modern science is. Now there's many pressures on us to become much more practical. We have to connect with society. Maybe we have to go out and help plant crops, or we have to employ thousands of people and make billions of become a crorepati. Whatever it is, the emphasis, the government, not just in India, but all over the world, the government would like to see us do practical things, would like to see us grow the economy. Now, in the heyday of science, probably from the start of the 20th century till about now, it was accepted that what was important was basic science. What we were interested in is learning for the sake of learning, not just in science, but any academic field, whether history, geography, biology. If you're looking for a cure for the malaria, for malaria, it's not necessarily because you're interested in finding the cure for malaria. That's a great thing to do, but you're interested in the problem. We do research. Why? Not so much because of the final goal, but because what's interesting to us is the research itself. It's the joy of finding out something new in what you're doing. You're looking at astronomical data, you're looking at your theory, you're looking at your models, you're looking at fruit flies, and suddenly everything falls together. And you say, oh, this is so obvious. This is a new way to look at this. And so that's what modern science is. And I think in many ways, it began with Nikolai Copernicus. And this is the Copernican revolution. I think there were the two great revolutions in human history. One was the Copernican revolution, and the other was the Darwinian revolution. You all know what Darwin did. He essentially he removed the hand of God from biology. Instead of God creating every species on the earth, creating humans in God's own image, everything comes out as a natural process through evolution. So note, I'm not talking about the existence of God as an abstract being. I'm just saying that there's no need for God in our daily lives. There's no need for us to say that apes were here, dinosaurs were here, humans were here, and God created them all. Now, what Copernicus did is that he postulated the heliocentric system. Before Copernicus, it was a geocentric system in which the Earth was at the center of the universe, and everything went around the Earth. Now, again, this is a gross simplification. What we do in science is that we identify people and we identify points. And so we identify Copernicus with the Copernican revolution. But there were many people before that who had postulated that the sun was at the center, that it was a heliocentric system. Science is not a linear stream, it's a web. And every little bit depends on everything that comes before, and everything that comes after depends on everything that we do. And this is why all this stuff about our ancestors having knowing everything about science, having atomic weapons, that's just not possible, because science is a web. You have a foundation. That foundation is broad with many contributors, not just white men like Copernicus, but many different people from many different cultures all contributed to this. And
Jen?
so when I say Copernicus, I'm just using Copernicus as a proxy, as a symbol of all these people who were there before and who were there after.
Jen, may I interrupt?
Please.
There is a question from Rishabh Pandey.
Uh-huh.
He is asking, what is Mayan calendar and Sunstone Aztec calendar used by CERN, CERN, CERN? Do you have any?
I actually don't have no idea what CERN is doing with this. And I would be cautious in where.
Please go on.
Okay, I would be cautious in where I get my information from, because there's a lot of stuff out there and not all of it is reliable. So I can talk about these other, I can't even really talk about the Mayan calendar. I know, what was it, 2012, there was supposed to be some big catastrophe. Obviously, nothing happened in 2012. And I guarantee you, no Mayan predicted the pandemic, nor did Nostradamus or whoever else you want. So there are different calendars. Every culture has their own calendar. And these calendars were largely brought about for religious purposes. They were there to predict various festivals, various events. And so what CERN is doing, CERN is a scientific organization. What they're doing with any Aztec calendar, firstly, I expect that they're probably not doing anything with an Aztec calendar. Secondly, if they are, it's probably some academic pursuit, seeing how how it relates to various events in Incan culture. All right, so I know that it's a wishy-washy answer, but I'll guarantee you that CERN is not doing anything scientific, let me word it properly, with the predictions of the Aztec calendar. They may be looking at its genesis, but that's about it. All right, so what Copernicus did is he moved the Earth from the center of the universe. And so here, I hope this video comes through okay. What this is the previous Ptolemaic system. The Earth is around the center, the sun is going around the Earth, and you see all the planets doing weird little circles, epicycles on epicycles. And so in order to model this, you needed many circles. Now, when you move the sun to the center, look how simple everything becomes. Everything is nice circular orbits. I mean, we know now it's not circular, elliptical orbits around the sun. And so what we've done is we've changed an ad hoc system where you take the observations and you have no theory to explain it, but you have an ad hoc system, and you for some reason, the planets go in little circles and circles and circles. Why do they do that? Well, you don't know. And now you changed it to a system where just simply by looking at it from the right perspective, from looking at it as if the sun was at the center, you now see that that there's a physical explanation for this. What it is yet, I don't know, but I know that the sun must be responsible, and the planets are going around the sun. Now, this was just the start. So Copernicus first removed the Earth from the center. But now the sun is at the center of the universe. So now what's the next step? Well, now we know that the sun isn't at the center of the universe. The sun is in fact a small star at the edge of the Milky Way galaxy. We know that the Milky Way galaxy is one of billions and billions of galaxies, that our own galaxy is nothing special. It's not the largest, it's not the brightest, it's not at the center. And so there's nothing special about humanity anymore. We're here. We're lucky enough to be on a planet that likes us. We don't necessarily like it back, but we're lucky to be on a planet that likes us. And here we are, but there's nothing else about it. The universe just doesn't even notice us. And
Jayant, one more question. Sorry.
Yeah, sure.
So from Vishwanath Mahapatra, will it ever be possible to create a calendar that will be perfectly in sync with our solar system?
Oh, we've done it already. And when you say perfectly in sync with the solar system, now you can have different calendars for different purposes. So our Hindu calendar, our Muslim calendar, our Jewish calendar, they're intended for religious festivals. So they're intended to tell you when it's time for Passover, when Shivratri is, when Ramadan is. So all of these there's a purpose for those calendars. Our solar calendar tells us that it tells us when the seasons come. So we know that the monsoon will come at the same time every year. If I were living in a snow area, I would know that the snow comes in December, or in the Southern Hemisphere, the snow comes in July. So this is the reason for the calendar. Now, we have different constraints. So you have a day. You might have different days. You might have a sidereal day where you look at the stars. You might have a solar day, which means that the sun comes up to noon every day. And we live our life by the sun. We want the sun to be overhead at noon. We want darkness to come between 7 at night and 5 in the morning, or whatever it is. So we live our life by the sun. And so what we want, but now we have these two different cycles. We have a daily cycle where the sun comes. We have a weekly cycle. We have a lunar cycle where the moon goes through, that's about what a month is. And then we have the yearly cycle. So when you put all of these constraints together, If you want your yearly cycle, it just doesn't, you just can't get an even number of days in a yearly cycle, right? So that's the basic problem. So our calendar now, it is matched to the sun, and we make it match to the sun simply by adding a few seconds here or there. So it's a matter of how do you define it? Our calendar is perfect. It's just that we change it every now and then to bring it in sync. There's no way you can get a daily calendar in sync with a yearly calendar, because a year is not an even number of days. You either lose the daily synchronization or you lose the yearly synchronization. You can have other types of calendars. Maybe you want a calendar in which the moon is in the same position. So that's a lunar calendar. Maybe you want a calendar in which the stars are in the same position. So you can have different calendars depending on your purpose. But finally, for us, the sun is the most important thing in the sky. And so that's why we go with our solar calendar.
So there are two more questions.
Mm-hmm.
So if you're willing, I'll read it out.
I have plenty of time.
Okay. So the first question is from Omkar Gupte. He's asking, even after acceptance of heliocentric model by Copernicus, why Tycho Brahe moved towards geocentric model?
Okay,
That's
let me talk about Tycho Brahe in the next slide. I'll talk about him.
Okay, then shall I take the next question? It's relevant to what you just said.
Yeah.
So the next question is Vinayak Sanil. He's asking, are we so much as lucky for existence? The anthropic principle merely puts us as simple result. If a universe exists, intelligent life at some point in time will or must evolve.
Okay, now this is a philosophical question, right? And so in a way, it's outside the remit of what we consider to be astronomical science. So the anthropic principle, what does the anthropic principle say? It says that because we are here, the universe must have specific conditions. And so we know some of these. If the fine structure constant is a little bit stronger, alpha is a little bit stronger, then you don't get whatever it is, nuclear fusion. If the gravitational constant were a little bit different, either stars would be too short-lived, or you would never get stars because you would never get that contraction. So we can use the anthropic principle to set limits on the parameters in the universe. And I read a paper long ago where they looked at all of the different parameters that you could have. And they said, okay, in these universes, imagine that you had a multiverse. This is all philosophical, right? So we can imagine whatever we want. So you can imagine different sets of conditions such that life exists. They may not be life like us, but life exists. So that's the weak anthropic principle. In fact, Fred Hoyle used this weak anthropic principle to predict the existence of a carbon transition. He said that this transition must exist, otherwise the sun wouldn't be the sun. And then when they looked for it, they did find it. So that's a weak anthropic principle. What it is a statement that because we exist, we know that the parameters must be within these bounds. Now you can have a strong anthropic principle. We exist and we force these parameters to be within those bounds. You can have a very strong anthropic principle. I exist, and so therefore the universe exists so that I exist. But let's not go that far. So now, so this depends on your preference, how far you go. So yes, we exist. And if you go by the strong anthropic principle, then our existence forced the universe to exist. The weak anthropic principle is probably more intuitive. It says that we exist and we wouldn't exist if the parameters were much different. So how far you want to stretch that is up to you. I don't go so far as to say that we exist and therefore the universe only exists because of us. To me, that's a violation of the Copernican principle. Okay, so I hope that answered that issue. I think it's more or less a philosophical question of what you want to believe. All right, so now let's move on to Tycho Brahe, who was the first of in some ways you can say the first of the modern observers. In some ways, he was the last of the old style of doing astronomy, because the telescope, he didn't have a telescope. He looked at the sky with his naked eye. And what he did was he cataloged stars. And he just looked up at the sky and said, star here, and he wrote it down. And he had such a good eye that he could position a star to within about an arc minute, which is about as good as you can do with your human eye. What an arc minute is, it's a little not so easy for me. I always forget, but the moon is about 1 degree in size, I think, about 1 degree in size. And so an arc minute is 1/60th of the size of the moon. An arc second, which is what the atmosphere lets us do, is 1/3600th the size of the moon. And I always like showing this because this is Tycho Brahe's observatory. And unfortunately, it doesn't exist anymore. It was demolished at some point. And this was, to me, it always looks like a vampire's castle. And you see the bats flying out from it. But this is where Tycho Brahe did all his observations from. And I always like to, one of the things about being a scientist, in my opinion, is that you're curious about many different things. And so I've always been curious about history, and I'm curious about the astronomers. So Tycho Brahe, he had a brass nose. In fact, he had an interesting life. He was when he was young, his parents gave him to his uncle. His uncle didn't have any children. I think his child had died, and so they gave Tycho to his uncle to raise as his own. Now, fortunately, his uncle was quite rich, and Tycho had a good life. And then when he went to whatever it was, he had a fight with another young nobleman. He was a nobleman, and he had a fight with another young nobleman, probably over a romantic interest. And he fought him in a duel. And in that duel, his nose was sliced off. And so he ever after that, he had a metal nose. And it's possibly apocryphal, but I've heard that he had several, sorry about the noise, several different noses. So he had a brass nose that he would use in his daily life, and he had a gold nose which he would use on ceremonial occasions. Now, so Brahe was, because his uncle was famous, he was a favorite of the Danish king. And so that's why the Danish king gave him this land and gave him this the money to build the observatory. And this is where he did his work. After the Danish king died, he didn't get along so well with the children. And so he left Denmark and went to Bavaria. And in Bavaria, he was, again, some court astronomer. And the story goes that that he was sitting at a banquet sitting at a banquet, and he had to relieve himself, go to the bathroom urgently, but he thought it was not very polite to get up, and so he continued to sit there. And the next day, he died of a perforated bladder. So these astronomers give us life lessons as well. Now, when he died, as the question said, Brahe himself was not a Copernican. He, in many ways, Copernicus himself, he didn't release he didn't release his book. Let's see, where is it? He didn't release his book on the revolution of the celestial spheres until his death. Excuse me, until his deathbed. As he died, he released the book, basically because he was basically afraid of the reception it would get. He didn't want to get in trouble with the Catholic Church. So Brahe himself was not a Copernican. He did not believe in the Copernican revolution. But he was a superb observer, and one should give him credit for his observing work. Not so much for his theory. He had these weird theories of music of the spheres, where all sorts of weird astrological stuff. But that's not the important thing. The important thing is his observations. Even though he was not a Copernican, he made wonderful observations, and those observations were then used by those observations were then used by Kepler. Another thing that Brahe did was he observed Tycho's supernova, and what it was an object that it was a new star, de nova stella, a new star, and the fact that it was a new star showed that the heavens were not unchanging. The heavens do change. It's not just a sphere up there with pinpricks where the stars are. It does change. And so it showed no parallax. And so that meant that it was further away from the planets. It was in the stars. We knew that the planets moved. We knew that comets came. We knew that meteors came. But this was a big object. It was a new object. And we knew that it was further away than it was with the stars. So it showed that the heavens do change. So now came Kepler. Now Kepler was a Copernican. He was a Copernican through and through, as was Galileo, who came right after Kepler. And what he did was he went and worked with Brahe as a student. And when Brahe died, Kepler took his observations and he ran away. In normal time, maybe Brahe's children would have taken his observations, but Kepler knew that he was much better than his children. It's a good thing for us in history. We're perfectly willing to condone theft if it happened for a good cause 400 years ago. And so he stole Brahe's observations and he went and analyzed them. Now, Kepler himself, he did have his astrological leanings, and there's a book that I want to read. It's on my list, where they talk about how he went. His mother, I think, was accused of witchcraft, and so he went and argued to try and save her. He had his own astrological theories and so on. But what he did was that he went through Brahe's observations and he looked at the motion of the planets. And he saw that the planets don't move in circles. In fact, if you look at the Copernican data, the heliocentric universe, the Copernican predictions for the planets were actually worse than the Ptolemaic predictions, because Ptolemy added extra spheres to make sure that the observations matched the data. Copernicus didn't. He just had circles, and so they got out of sync with the data. So what Kepler did is that he looked at the positions of the planets and he went through various ideas, various theories. Now, remember that this is in the pre-computer days. And so he went through it by hand. And you know, I've done this in the past. My own colleges before computers really came in. And you'd go through and I would always get confused. My handwriting is bad. And so I would get confused. Is an A squared, am I writing an A squared or am I writing a 2 to the A? And if I'm writing pages and pages of calculations, I make mistakes. And I'll always make mistakes. And Kepler did that. He made mistakes. And what he found when he made mistakes was that his theories didn't match the data. And he was so confident that Brahe was correct And this is what I mean when I say Brahe was a great observer. He was so confident that Brahe was correct that that he changed his theory in order to accommodate Brahe's, in order to make sure that it met Brahe's observations. That was in agreement with the observations. And so what Kepler said is that planets move in ellipses with one focus at the sun. Now, when I say it like this, it sounds easy. And this is true of most great discoveries. It's that you think in a box. You thought for all your life that planets move in circles. A circle is a perfect shape. And so all the planets move in circles. So what is the great thing that Kepler did? Move the planet circle to an ellipse? Well, that's an epiphany. It's something that no one had ever thought of before. But now Kepler said, oh, what if I just change this one thing? Change a circle to an ellipse. And again, now it sounds easy. Why not try an ellipse? Why not try a parabola? Why not try a square? Try whatever you want. But this broke that mold in the same way that the observation of Tycho supernova showed that the sky was not unchanging. It broke that paradigm. Kepler broke this paradigm of circles. And so that is real genius. It's when you go through and you suddenly say, well, maybe everyone before me was wrong. Maybe if I make this change, everything will work out. And so I'm not going to go through Kepler's laws in detail. 3 laws, and this applies everywhere. This applies to our planets in the solar system. This applies to stars going around the black hole in the center of our galaxy. This applies to clusters of galaxies where the galaxies all orbit their center of mass. Any scale you want, we have Kepler's laws. Until you get to the,
Sorry to interrupt. Okay, so there is a small clarification. Aman Swankar is asking, what does heaven mean here?
Heaven's a sky. I use heavens interchangeably with sky. Something way out there. I'm not trying to be literal and say there's a heaven up there. Stars in their heavens. Okay, so I hope that clarifies that. Okay, so what did Kepler say? He said the planets move in ellipses with one focus on the sun. Equal areas are swept out in equal times. And what this says is that if a planet, and this applies, as I said, to satellites also, and we use this in satellite observations. When the satellite is close to the Earth, when the planet is close to the sun, it's moving fast and it sweeps out a big angular distance. When it's far from the planet or from the sun, it'll go much more slowly. And so, if we look at a spacecraft such as the Infrared Space Observatory, ISO, is that its name? Anyway, what it did was they wanted to be out far away from the Earth, where it's much colder, and they didn't want to observe near the Earth. So what they did was they had a very elongated orbit where one side would come right by the Earth and it would just whip through that in a few minutes, and then it would go way out to the far extent of the Earth of its orbit around the Earth, and it would observe from there where it was cold. Okay, and the last of Kepler's laws is the square of the period is proportional to the cube of the semi-major axis. And I won't go through this in detail, but I will just say that when Newton came along, he used the Kepler's laws to formulate his law of gravitation.
Okay, before you move on, another question related to Kepler's laws. So Gopal Chetty Brahma, his question is, will Kepler's laws be applicable to 3-body and multi-body systems where the bodies have a significant influence on the object of observation?
Well, Kepler's laws are really just a statement of gravitation. And so what if you have the solar system, Kepler's laws will apply. If you have a star come by and perturb the solar system, then no longer. I mean, this is you have the basic assumption behind Kepler's laws, and you can correct me or maybe clarify what I'm saying, Prava. The basic assumption is that you have a big body that dominates the gravitational field in the area. So you have the sun, which dominates the gravitational field in the solar system. If I have another star come by, then again, gravity always applies. But as long as you use the center of mass, Kepler's laws will always apply. Is that right, Kepler?
Yeah, that's right. So
as long as you use the center of mass.
Two or more bodies, they will revolve around the center of mass.
Yeah.
Their trajectories.
In
Then
fact,
there will be gravitational GR corrections too.
yes, of course. This is all Newtonian mechanics. No sign of relativity. Okay, and I should
Sorry, one more question.
Yeah, let me just add one thing here, Prabha.
Okay.
If you actually, there was an interesting video that I saw, and you can search for this. If you look at the motion of the sun, it's actually not around the solar center. You watch how the sun moves, and because of Jupiter, primarily because of Jupiter, the center of the solar system is not the center of the sun, and so you can watch the sun move around. The sun goes in a small orbit around the center of mass. It's a fascinating picture. Look at it. Look for it on YouTube. I'm sure it's there. Yeah, sorry. Go ahead.
There are a few questions. So Tushar is asking, could you please elaborate the model adopted by Tycho Brahe? I have heard about heliocentric system. What does that exactly mean? Then there are a few more questions, so I will let you decide whether we should take questions, more questions.
Yeah, sure.
Okay.
We can take the questions, but let me answer this question.
Yeah.
So Brahe himself did not believe in the heliocentric system. Now, the system exists whether you believe it or not, but Brahe still believed in the Earth system. So I think he had a funny system. I'm not an expert on this, but I think Brahe's system had the Earth going around the sun and then the other planets going around the Earth. And so it was a really complicated system, and I don't think he ever got it to work properly. So no, I can't. I don't know much more about it than that.
Okay. Shall I read out other questions?
Please.
Okay. Omkar is asking, can you tell the name of the book of Kepler and his mother's story? So maybe you can add.
I'm sorry. I have it saved somewhere. I'll look it up.
Okay.
I'll let Prava know, and maybe you can put it in the notes or something.
Yeah, sure.
By the way,
next
you know that Kepler was the first science fiction author. What was it? He wrote a book on people going to the moon, if I remember right.
Okay, next question is from Gautam. When Kepler formulated his laws, did he have prior knowledge about gravity and gravitational fields?
No. And this is where Kepler was purely observational. And so what he did was he formulated he observed how the planets moved. Right? So he didn't say why the planets moved the way they did. Or, I mean, I don't know what his theory was. I don't know if he had a theory, but he was trying to explain observations. It wasn't until Newton came along and they postulated the force. So this is the way that things move along. People observe, try to explain the observations, try to parameterize the observations, try to explain the observations. I don't think Kepler himself had any knowledge of why Kepler's laws applied.
Okay, there are a couple more questions. So KPM Palani Mittu, he or she is asking, an ellipse needs two centers if the planets revolve around the sun in an elliptical path and the sun is one center. Then what is the second center? That's the question.
Well, I don't know if there's any specific rule. How the planets move in the orbits they do is to a large extent statistical. The planet, it moves in an ellipse. It just so happens that an ellipse is defined so that you have two foci. But I don't think there's anything physical about the other focus. It's simply a way to describe the orbit. And how much of an ellipse the planet moves in will depend on its initial conditions and how much dynamical friction you have and so forth. Is that right, Prabha?
Yeah, I guess.
Yeah.
So there is one more question. There's a comment which probably I'll not read out. This is the barycenter of Sun and Jupiter from Gopal Chetty. But there is one more question. This is about Tycho Brahe. Heliocentric system were so good at explaining how was Brahe so correct with his observations as he believed in geocentric system. This is Karamchandani Megha.
So let me separate the two. What Brahe did is that he made a star catalog. And he just said that all the stars, this is where the star is. You don't need a model to do that. If I go out, I can catalog every leaf in that tree outside my house, but I don't need a theory for that. I'm just making observations. And so that's all that Brahe did. He made observations and he wrote down the position of every star. In a modern era, I would have a camera and I would take a picture of the sky. That picture of the sky doesn't depend on any theory, geocentric, heliocentric, cosmocentric. I mean, it doesn't depend on anything. It's just the way the sky is at that point in time. That's all that Brahe did. I mean, I say now that's all that Brahe did, but no, it's a labor of a lifetime. And for him to do it in the time that he did, without any benefit of telescopes, without any benefit of computers, it's awe-inspiring. But it did not rest on any theory. It was simply observations. And again, when I say simply observations, I'm not trying to denigrate it in any way because it was such a immense task, but that's what he did. Okay, not observational at all. I mean, not theory-based at all. He had his own theories afterwards, but that's separate from his observations. Let me also, this is a good time to just talk a little bit about the philosophy of doing science. You do have different things. We have different kinds of astronomers now. I consider myself an observational astronomer. We have many different descriptions. And a UV astronomer. I do my work in the ultraviolet. I do my work from space-based data. You can have theorists, for people who work out equations. When you work out equations, these equations have to describe the data in some way. But your equations don't govern the data. Asimov once said that if your models don't describe the universe, you'd better change your models because the universe isn't going to change. And this is what Brahe did. He had data. Then he had his models, but his models didn't predict his observations. So his models must be wrong. And so this is what we do. It's a constant battle. We create models. Maybe we even believe our models. But finally, if the models don't explain the data, then you have to change your models. And that's the way it is. Now in the modern era, science has become so big that we can't possibly understand everything about science, nor can we do everything. So one of the things I've done is that I was very interested in diffuse radiation. And so I spent 2 years going through the entire galaxy database, extracting all of this diffuse radiation in the sky, the way the sky background looks like. And while you're doing that, it's a full-time job. It doesn't let you have time to think about why. It's only after you do that bit that then you think about it. And this is Brahe's situation. He created the atlas of the sky. And then what he thought about it, well, that superseded. The sky observations, they survive. If we want to look at the sky at the time of Tycho, we can still go back to his data and understand what it is, what it was like at the time. Okay, any more questions, Prabha?
Yeah, there is one more question.
Mhm.
Okay, this is from Arijit Mondal. He's asking Kepler's laws, orbit, planetary motion, all these are 2D motion. Should it not be 3D? Because planets are spherical in shape, space is also 3D. I am a bit confused about 2D or 3D planetary motion.
Yeah,
That's
so of course they're all three-dimensional motions, but if you actually look at the solar system, it's almost two-dimensional. The ecliptic plane, almost all of the planets move more or less in the ecliptic plane. And the reason for this is because if you have a sphere rotating, when the solar system formed, you had it formed out of a sphere. Particles were moving in all different directions in the sphere. Eventually, the other directions, the particles kept colliding, and everything else canceled out, and all you were left with is a plane. So yes, it is a 3D description, but the planets themselves essentially move in the orbital plane is two-dimensional. You can look at the solar system, and the planetary motion, the planetary orbit, is two-dimensional in a three-dimensional system. You don't need to have 3D geometry to describe the motion of the Earth or Jupiter or anything else, at least to a good approximation. Once you start looking at perturbations from the Jupiter, look at the perturbations of Jupiter on Earth's orbit, then sure, you can start looking at you can start looking in 3 dimensions. But it doesn't make much difference mathematically anyway, because these are all transfers to each other, so it'll all add up. Okay, I have about 20 minutes left. So let me go quickly through, and then I'll take the remaining questions at the end of the talk. Okay, so I'll go through a little faster. So the first of the modern astronomers was Galileo, and what he did was the first person to look at the sky with a telescope. Of course, he wasn't. We know that people looked through the sky with telescopes before him. Telescopes have been around for centuries before Galileo. People knew that you put two lenses together, you could see ships coming the way. But what made Galileo important was that he wrote down and he popularized everything that he did. And so this is another critical thing another critical part of being a scientist. We have to communicate what we do. And that is why we celebrate Galileo. Not necessarily that he was the first person to do it, but that he was the first person to do it and actually talk about it. He went to the public square in, in Genoa, I think. He went to the public square in Genoa, and he gave talks, not in Latin, which was the language of science, but in Italian, so that people would listen to him. People could understand what he was saying. He had his newsletter that he would put out, the Sidereal Messenger, that again, where he would spread it out to his patrons and make sure that everyone knew about what he did. So Galileo, first person to look at he saw sunspots, first person to see sunspots. He observed the phases of Venus, which showed that Venus was between the Earth and the sun. He observed satellites around Jupiter. And what this did was that it showed that it showed that not all objects in the solar system orbited the Earth, orbited the sun, or orbited the Earth. There was satellites that went around Jupiter. And so this is just an animation of the stuff that he drew. Again, this is pre-photography. So he drew all this. And this is, if you put it together in an animation, you saw how the planets moved in his version. And this is a modern observation of Jupiter. So observe the moons of Jupiter. And so rightly so, in 2009, the 400th year of his first observations with a telescope. As I said, he was not actually the first, but he wrote about it. People know that Galileo observed the sky with a telescope. 2009 was the year of astronomy. Okay, and then finally, we get Newton. And this is quoting Samuel Johnson. Nature's laws lay hidden in night. God said, let Newton be, and all was light. And this is his famous separating white light into a prism. And again, we celebrate Newton for the things he did. We celebrate him for his work in optics, for his work in gravity. We don't celebrate his alchemy. You know that he was knighted. He wasn't actually knighted for his scientific contributions. He was knighted for his work in as treasurer of the mint. He made sure that the English currency was harder to counterfeit. All right. So now, after Newton came, this is now we have modern astronomy. Now we have observations. We have theories. People try to understand. People do astronomy for the sake of doing astronomy. And so now you have the discovery of the remaining planets. You have the discovery of Uranus. This was William Herschel in 1781. And Uranus is actually naked eye. It turns out that Galileo had observed Uranus, but he didn't recognize it as Uranus. Again, paradigm shift. There were 5 planets. And so it wasn't until Herschel said, hey, this is a planet, that people said, oh, okay, maybe there's more than 5 planets. Maybe there's 6 planets, 7 planets, 8 planets. And so Herschel discovered Uranus. It looked comet-like through a telescope. And he knew where his money came from. He knew that he was funded by the king. This is George III. And so he said, well, why don't we call it Georgium Sidus? George's star. And naturally enough, the French and other Europeans didn't particularly like this idea. So after a while, they said, well, the other planets are named after Greek gods. Let's name this after a Greek god too. And so rather than Georgium Sidus or George's star, they called it Uranus. After Uranus, they kept observing Uranus, and they found that Uranus didn't follow Newton's laws, meaning that they would look at it for a while, the orbit looked very nice, but then they look at it 50 years later, and the orbit is no longer a nice ellipse as you would predict from gravitation. And so Adams and Leverrier, Adams in England, Leverrier in France, they said, well, maybe there's another planet out there. And that is what is changing. That's what's affecting the orbit of Uranus. And so this was the first planet that was discovered by the point of his pen. This was discovered by Leverrier. And what he did was he went through the calculations and he said, okay, maybe there's a planet out there. and what he said is, if that planet exists, it must be here. And so when he went to his friend Gale at the newly formed Berlin Observatory, and he said, look there. And when Gale looked, he found Neptune. And so this was discovered purely by theory. Adams, it turns out, had, you look at the stuff, maybe it was here, maybe it was there. And it turns out that when you look at he had also told the Greenwich Observatory, he said, you look there, but they hadn't analyzed their data. And so when they went back and reanalyzed the data, they found Neptune. But by that time, Galilei had already said it was here. So Leverrier gets the credit. The British, they complained a lot. They always complain a lot. And the French opinion of this is in this cartoon here. Here is Adams over here. And I'm sorry, here is Leverrier looking up at the sky. And here's Adams over here looking at Leverrier's calculations. So they were not at all happy. And but now whoever gets credit, as I said, astronomy is a web. Adams himself, he always gave the credit to Leverrier. He said he found it, and he deserves the credit. But whatever, there was Neptune. Now there were still variations in Uranus's orbit that were not predicted, not accounted for by Neptune. We know now that these were simply errors in observation. The techniques were not so great at the time. And so these were just random or systematic errors that changed that the orbit was not where it was, and that Uranus was not quite predicted properly. But Percival Lovell, who was famous for discovering the quote unquote canals of Mars, which were later to be found to be optical illusions. Probably he looked at Mars too long. He insisted that there was a planet X, and he left $1 million to continue the search for this planet X. And so there was a little problem. His wife didn't believe. She thought she could use the $1 million better than the observatory. But after a little time, they came to an agreement. And Clyde Tombaugh discovered Pluto in 1930. And this is the discovery photograph. This is how Pluto was discovered. And fortunately, there are arrows to tell you where. When you look up at the sky, if you look up at the sky and you see an arrow, it's always a good sign there's something interesting there. And so here is Pluto in January 23rd, and here's Pluto 6 days later. And you can see how faint it was, hardly visible at all. And then when they looked back at previous observations, they could trace it back to observations all the way back to 1900. But here's Pluto. And I'm not going to get into the Pluto's Pluto a planet or not. That's a completely separate talk. So let me take a small diversion here. Astronomy is, as I said, the oldest of the sciences. And so we have some historical baggage. And one of these is the magnitude scale. And so the magnitude scale came about because the Greeks classified stars by the brightness to the eye. And the eye is a logarithmic scale. They magnified the brightest star. They classified the brightest stars as 0th magnitude, and the faintest stars were then about 6th magnitude. And so each magnitude corresponds to a factor of about 2.5 in brightness. A factor of 100 is 5 magnitudes. And so the sun is something like minus 26 magnitude, and the faintest star now is maybe minus 30 or so. So the magnitude scale, as you go higher, you go fainter. And so we had Galileo. Because he looked with a telescope, he could see fainter objects. And because there are always more fainter objects than brighter objects, it's again logarithmic. You go fainter, you can see a volume that's much bigger. And so what Galileo did was he went fainter, and now we go to fainter and fainter, larger and larger telescopes, and we see fainter and fainter objects. So one of the things you do is by going deeper, but it's not just going deeper. the next great, but Galileo, he still had to draw what he saw in the sky. And so we depend on his drawings. And so for people who are maybe not as good drawers or not as good artists, your sky is not as it may not be an accurate representation of what you see. So the next innovation is photography. And so this is the first daguerreotype of the moon. Daguerreotype is the early photography. And this was made by John Draper in 1840. Daguerre himself, I think that's his name, after whom the daguerreotype is named, he actually did observe the moon the previous year, but he couldn't make any good pictures. It was all blurred. So John Draper observed the moon with the telescope, and you see it's not great, there's all sorts of artifacts, but he observed the moon and he made a picture of the moon. So we can now take pictures, we now see what the sky was like all the way back to 1840. And we can do historical astronomy. So we look at photographs of the sky back, maybe not to 1840, but at least back to 1900. And we can look at what's changed. And there's some wonderful observations of the Crab Nebula in which you can actually see the Crab Nebula expand over the century since it was first observed with a photographic film in 1900. And now modern astronomy just uses better instruments, better CCDs are basically just better photographs. We have spectrographs, we have electronic detectors, but in principle, it's all the same. We're looking at the sky through better and better telescopes, through deeper and deeper, through better instruments. And so we look at things with radio telescopes. This is GMRT. And this is our own astrosat. We want to go out over the atmosphere. Why? Because the atmosphere obstructs much of what we can see. If I want to look at X-rays, if I want to look at gamma rays, if I want to look in the UV, which is what I do, you have to go above the atmosphere. Moreover, the sky does other things that because you're looking through the atmosphere, you get twinkling. And so again, you want to go above, and many of the greatest pictures, many of the best looking pictures of the Space Telescope are not in other wavelength regions, not in the UV or infrared, but rather because you're going up above the atmosphere and you get so much better resolution. And so all of these techniques I'm not going to talk about. I'm not going to talk about the advances in adaptive optics, where I'm not going to talk about TMT, the 30-meter telescope that we at IIA are involved in. We're building some of the mirrors from that. All of that you may get in other talks, or you may search for it by yourselves. But these are all they're not paradigm shifts. They're just building better detectors, better instruments. And one of the things that overview of astronomy, there's so many things that I could talk about. I wouldn't be doing justice to any of them. And astronomy, after the Hubble Space Telescope, we now understand so much more about astronomy than we did. COBE, the 3-degree background, now there's no real alternative to this idea that the universe started in a Big Bang. And so again, I hope you'll see some of these in the following talks, but I won't be showing you these. The one I chose is this orrery from Kepler. And what this did, Kepler just looked for planets. And the primary purpose was to look for Earth-like planets around sun-like stars. But here is a medley of all of the different planets that they found. They found Jupiter-sized planets that were bigger than Jupiter, orbiting their star closer than Mercury orbits our sun. When I was doing my graduate study, this was in the early 80s, from 81 to 86, there were no extrasolar planets. The first extrasolar planet was discovered in, I think, 1986, and that was a planet around a pulsar, 1986 or 1987. Planet around a pulsar. The first planets around normal type stars were discovered in the 90s. That was the Nobel Prize of I think last year, Mayor and anyway, whatever. So it was not while I was a graduate student, there were no extrasolar planets. We thought our solar system was a typical solar system. We didn't even know if other stars had solar systems. Now we know that there are planets everywhere, and we know that our solar system is perhaps the oddball in that we understand it. It makes so much sense. Hot, rocky planets near the sun, cold, Jovian type planets around far away. Okay, so that's what I chose as my astronomy takeaway. And let me end with this slide, which is the growth of astronomical data. Now, we started with naked eye astronomy. People wrote down their observations. Everything was handwritten. Everything was plotted on the sky. Now we have larger and larger instruments. We have larger telescopes, more sensitive telescopes. We have bigger ways to record it. And all of this is recorded electronically. And so all of this data, this has caused a paradigm shift in the way we do astronomy. Now, no longer do we have individual astronomers sitting with their data. You open your desk drawer and you pull out your photographic plate and you say, I'm not going to share my data with anyone. Now we have terabytes of data, exabytes of data, petabytes of data that are just sitting there. And there is no way that scientists, not just in astronomy, but all of science, there is no way that any scientist can look at all of this data. And as a paradigm shift, this data is now all available, and anyone can look at it. You can, in some ways, these have been formalized. The Kepler data, you have planethunters.org, you have galaxyzoo.org, where you can go and you can look at the latest astronomical data, and you can try to use it for your own purposes. And so this is where we are moving. We're not there yet, but hopefully we'll move to the time when every astronomer or anyone who's interested can get data from anywhere they want and look at it on their desktop. And so this opens up opportunities for people at an individual level, for people at a department level, at a university level. We can have involve students in our projects. And so all of this is not quite there yet, but hopefully this is coming in the future. So let me end here, and any further questions, happy to take, or as long as your schedule allows.
Thank you, Jayant, for a very wonderful walk through history of astronomy. So there are several questions. So I have to apologize to people because we don't have too much time. So I am going to pick and choose questions, okay? So I apologize in advance. So there was one question in the beginning. Yeah. Okay, that is a more... So Deepak Pandey is asking, do Indian ancient astronomers did they have any relevance in progress of modern astronomy?
So
that's a more general question.
As I said, we like to think of a linear progress, but it's not that way. We know that there was an exchange of knowledge everywhere, and unfortunately, I don't know very much about it, and I think that I don't know the solid historical studies, not the wishy-washy nationalistic studies, the solid historical studies that trace these connections. But yes, everyone talked. The knowledge went out through the Silk Road. There was an exchange of knowledge everywhere. We know that. And so, yes, there was exchange. I just don't know how to quantify that.
Okay. So the next question that I will read out is from Aditya Suresh. He says, okay, the stars and moons, they are very far away, where its shape is not clearly visible. How is it concluded that they are circular? Even before knowing about center of gravity, did they have any theory? Did they have any theory about its shape?
Well, the circle doesn't come from gravity. The circle comes because the circle was the perfect shape. Now, why was it a perfect shape? I don't know why it was the perfect shape, but a circle is a perfect shape. And so it was just assumed that everything was a circle. And it more or less is. The orbits of the planets around the sun are almost circles. The Earth is almost a sphere. Now we know why, but it's almost a sphere. If the Earth was an apple, I've forgotten the comparison, but if the Earth was an apple, Mount Everest would be no more than the thickness of the skin or whatever it is, almost. So it worked out.
Okay, so I'm going to pick the next question from Saurabh Bhattacharjee. And he's asking about, please tell us more about Newtonian reflector. What kind of advancement it has that Galileo's telescope did not have?
Okay, do you have a talk on this later or?
No.
No, okay. So the Galilean telescope, the refractor, you have the way you make telescopes more sensitive is that you make the lens bigger. You make their collecting area more. So the amount of light that falls on the telescope has to be increased. Now, the trouble with a refractor like Galileo is that you have lenses. And as you make the lens bigger, you have two problems. One is you have to have a perfect lens, because any holes or any imperfections in the lens will affect your image quality. And the second thing is you have to support that lens somehow. So let's say I want an 8-meter lens. That's going to weigh, I don't know what it weighs, maybe a couple of tons. And I'm supporting it by its edges. So you're going to get all sorts of gravitational effects, gravitational sagging. As you move your mirror around the sky, you'll get gravitational sagging. You'll get stresses on the edges. So you have these practical limitations on lenses. If I have a mirror, I don't really care about the back of the mirror. I don't care about imperfections in the mirror. All I need is a smooth surface. And so I can support the mirror better. I can lightweight the mirror by digging holes in the back. Again, as long as the surface is good, what do I care? So you can have larger reflectors. Now for modern reflectors, now you can't really make a 30-meter mirror because again, that's going to be so hard to handle. So now you make segments. And you can do that with reflectors again, because as long as you make them on the right curve, you don't care so much about how the individual segments are built. And so you can have maybe 2-meter segments, which are so much easier to handle. So the basic reason is reflectors are just so much easier to make bigger because you don't have to worry about imperfections. You don't have to worry about gravitational stresses.
Okay, so we have very little time left. So there are a couple of questions that I will choose from YouTube. So first question is Adarsh Kumar Gupta. How artificial intelligence and machine learning help astronomy to evolve?
Yeah, I think it's a very good question. And eventually we have to move towards that because as we get exabytes of data and as we get gazillions of objects, how do you pick out the interesting things? Now, the problem I still have with this on a practical level is that the machine people and the astronomers talk different languages. And it's very hard to get it so that you want to choose your machine intelligence to make sense physically. And that I don't think has really happened as yet. So I think there's a lot of future there, but I don't think we're at the stage where the machine intelligence is very good at predicting what we already know. I think predicting new things, I think that is still a work in progress, but a lot of promise.
Okay, so this will be the last question. Arvind is asking, what program did you use to simulate the solar system? Can you suggest a good program software to play around with?
Yeah, there's this Universe in a Sandbox. That's the best one, as far as I know. Universe in a Sandbox. And so you can try all sorts of different planetary systems. And it's actually a useful learning thing. And I've done this because I thought it would be easy to do. So I wrote a little system I wrote a program to predict the motion or to calculate the motion of this Earth around the sun. And, I couldn't do it because you run into precision issues. It works fine for a short time. But as you go for longer and longer periods, you have to make your time interval short, because the way you do it is that you use the Newton-Raphson method. You take your circle and you take tangents to the circle and you calculate the instantaneous acceleration due to gravity at each instant. And so you need short time segments to make sure that you're always tangential, but then you have so many time segments over a long period of time that your computer precision just runs out. So these guys use all sorts of tricks to work out these giant gravity simulations. So I think it's instructive to write your own, but Universe in a Sandbox does a good job. And we use that for our, we wanted to calculate, we wanted to work out how Leverrier figured out the orbit of Neptune. Papers just published, by the way. And so we started with Universe in a Sandbox.
So maybe Jen, you can write it out, the name in the chat box. Many people are asking for it.
Yeah, Universe in a Sandbox.
Universe in a Sandbox.
Yeah, SANDBOX.
Okay, so let us close the session. We have gone a little over time, but that's okay. We have a long break now. So thank you, everyone. The next session will start at 11:20.
Ma'am, attendance sheet.
About that, I had mentioned in my mail that it will be sent at random. Okay, so please hang in there. We'll share it.
Ma'am, I thought each session will have attendance sheet. So.
No, we'll do it at random. So we'll circulate it. Right? So don't worry about it. Okay. So this link will be on. This link will be on, and you can log out or you can come back. It's up to you. But we close the session now. Okay. Thank you, everyone.
Right. Thanks for attending.
Thanks, Jayant. Very nice. Very nice talk. I learned historical things.
Yeah.
Thank you, Jayant.
Bye.
Okay, I'm done with that, Prabha.
Yes, thank you, Ishwar. Yes, first session is over. Next session will be chaired by one of the 3 volunteers.
Great.
Yeah.
Ma'am, the same link or a different link?
Sorry?
The same link for the meeting or a different link will be shared?
Same link. This will be on. Only at lunchtime we'll take a break, but this is the same link.
Prabhat, someone has asked for the PPT, so I'll send that to you.
Yeah, sure. Yeah. The YouTube YouTube channel, yeah, those also will be available after the school. We'll make it public. But yes, PPT is fine. I can share it. Yeah.
So, Prabha, I have to give you the next one.
Yes.
Are you
Yes,
going
Raj.
to close and reopen, or it's
No. This is open. It is on. You can test your slide, Rajguru.
Yeah, fine. Let me try sharing mine.
Yeah.
Host disabled participant screen sharing. You make me
You
a
need to
co-host.
Yeah, Crispin will do that.
Crispin?
Yes, I'll make 1 minute.
Okay, let me try now.
Yes, now assigned.
I will, should I try the whole desktop? Anyway, let me try.
Yeah, fine. If you open the PDF, yeah, yeah, it's coming. Only full
I mean,
view.
let me see if I can play the full screen. Is it all right?
Yeah, fine. Yeah, perfectly fine.
Let me see if I can. How do I make it?
Yeah, fine. This is full screen only.
Yeah, I don't want to make it full screen for myself, but I don't know how to do that. But any idea how I can
Now
remove
movie
the
is
full
playing.
screen for myself, but full screen for everybody else? No, I'm saying just the
Now
Zoom.
movie is playing. Let it over. Uh, you can put a escape button.
No,
No, escape button will work.
yeah. You see my screen still?
Yeah, yeah. Astrophysical context. Yeah. Now it
Fine.
is.
Okay. Let me just stop and share only the application and then whether it works fine or not. Okay, let me try again.
Yeah.
You see it now?
Yeah. Yeah, fine. Now it's full screen.
Okay. I mean, all right. Okay, fine. So we start at 11:20, right, Prava?
Yeah, so it will start at 11:20. The chair of the session is going to be Satab Dua.
Okay.
Yeah, if do you want can you take questions in between?
Yes, if there are any, pressing question on what I talk directly related to what I talk, you can allow them.
Okay. Satab Dua can interrupt you and he will read out the questions. So we are asking people to type in the chat box.
Okay,
And
they are not allowed to unmute and ask.
that may take a long time because number of participants is large.
Fine.
So
Okay.
there are many questions. In the last session, I had to pick and choose questions.
Okay, fine.
I think we may wait for a couple of minutes. People are still joining. So, Rajaguru, we have around 130 odd participants. Would you like to start, or would you like to wait a couple of minutes more?
Sadapto, it is at 11:20, right? We'll wait till 11:20.
Okay.
Yeah, let us wait. Let us start at the given time.
Yeah, but he can share the slide just showing.
Yeah,
Yeah,
the slide.
but I thought Shatabtu was showing the program. Is it? Can I share now?
Yeah, please share.
Yeah.
Satabdua is not showing any program. We are
No,
just
the schedule. Okay, anyway, so he was, now he stopped. Yeah.
No, I'm not.
No, just to fill up the blank screen I showed it.
Yeah, Crispin was sharing it.
Oh, okay. You see mine?
Yeah, it's visible.
Yes.
Okay. Yeah, so we'll wait for a minute or so more.
Sure.
So will you make it full screen, or you'll show? Like
I will make it full screen after when I start.
Okay, fine.
Maybe I'll make it now. You see the side window, is it, in your?
No, we don't see it.
No, not now.
So, Shatabtua?
Yeah, okay.
Yeah, you let me know when to start.
Sure. I think it's time, right? In my watch,
yes,
it's 11:20.
go ahead.
Yeah.
Okay. So, Shatabtua, just give me 5 minutes warning for the 1 hour.
Sure.
And then, yeah.
And
All right.
you would like to hear the questions in the middle of the
Yeah,
chat?
yeah. So if there is any pressing question on what I talk directly related to what I say,
Yeah.
you can post them to
Read
me.
them out. Sure, sure.
All right. Okay. Okay. Let me
Okay.
start. Hi. Good morning, everyone. My name is Rajaguru. I am a professor here at the Indian Institute of Astrophysics. So the topic, general topic given was solar physics. So there are 2 talks in solar physics. So I will cover some general introduction to the sun, and then I will cover mostly the solar interior, the structure and dynamics, and helioseismology, how we study the interior of the sun. Okay, I have given some references. I hope you can find them somewhere. There are certain, the first one and the fourth one are available online. It's free. The other two, number 2 and 3 are books, which you can get from a library you have access to. All right. Okay. So I understand most of you are in your master's degree. So I hope what I cover should be accessible to you. All right. Okay. Okay. Let me begin by showing you this video just to motivate why we care, why we study about the sun. So the reason is that we live with a star. Sun is our star. Sun, as we know, supports all life form on Earth. All the energy we get for all the life forms is from the sun. And its sun is one of the astronomical objects which has direct relevance to our daily lives. Okay, so studying the sun, as we'll show you a little later, it has a lot of implications for our technology in space and as well as supporting life on Earth. Okay, so this living with a star. So actually the NASA has a program called Living with a Star. All its programs to study the sun come under this program in NASA. So it's a very nice phrase, living with a star. Okay, so that was a small, simple animation I showed, showing from the Earth and the sun. And then let me give you a little astrophysical context. So the sun is part of, as you all know, we are in the Milky Way galaxy. So on the left, you see a nice picture of a Milky Way, a real photograph of the sky, a long exposure photograph. I think it was taken somewhere from Australia. So you see the Magellanic Clouds too here, there. So we are actually, if you just somewhere in the middle of this picture is of the Milky Way is the galactic center. So from our viewpoint, it looks like this. On the right is a simple cartoon picture which shows where we are on the galaxy Milky Way. So as you can imagine, sun is just a small part of the huge Milky Way. It's billions of stars and a lot of gas clouds in between. All right, so that is the astrophysical setting. So then what is a star? So you can, before we really talk about the sun, you can imagine a star as we understand now, the sun must have formed from a gas cloud to start initially, and it slowly collapses and then it forms a disk around it. And then after some time, the star, the central massive object becomes a star, and then the planets around it. So you can call it as a temporary triumph of nuclear physics over gravity. I will explain to you a little later. Basically, a star, what I mean here is that temporary triumph of nuclear physics over gravity means that the sun shines because of nuclear reactions happening at the core of the sun. And gravity always tries to collapse, always, gas clouds always collapse under its own gravity. And you need to have some energy to push it outward. And the energy comes from the energy generation in the core. And that increases the temperature and produces the gas pressure, and it holds. So it is a very nice balance of gravity against gas pressure. The gas pressure is due to temperature, and the energy is generated at the core of the sun. So most of the stars, which as we know, are due to this balance of gravity and gas pressure. Okay, so let me give you a little more astrophysical context. So sun is called yellow dwarf in terms of spectral classification. I think in some other lectures later, people will talk to you about the basic astrophysics or astronomy involved in classifying stars. On the left, what you see on the left diagram is called the HR diagram, Hertzsprung and Russell diagram, where we plot in the x-axis temperature. It increases towards the left. The color basically indicates the temperature. Red is little cooler and blue is hotter. And the y-axis is the luminosity. Okay, it is in solar units and solar luminosity units. So we normally see a horizontal, a diagonal patch under which most of the stars fall with decreasing temperature downward. And that is called the main sequence of the stars, and the sun somewhere in the yellow region, somewhere here. And we will not, later somebody else will discuss to you about basics of stellar astronomy. And little more here on the right side, the pictures compare the sizes of stars, all types of sizes you see. So the sun is called a yellow dwarf. It is a very smallish star, but there are stars which are much, much bigger, 300 times the size of the sun. For example, is a red giant. These are called red giants. So there is a range of sizes. So that gives you a little astrophysical background and little more on stellar life of a star. As I earlier mentioned, there is a gas cloud out of which stars form. If it is lower mass, like sun-like or lower than the sun, what we call as a sun-like star, and it slowly evolves to become a red giant. If the star is massive on the right part of the diagram, it evolves very quickly. A massive star evolves very quickly and becomes a red supergiant quickly and then explodes as a supernova. The sun will slowly expand after about 10 billion years. It will become a planetary nebula, and then the remaining, some mass will be ejected from the center, and the remaining part is called a white dwarf. Okay, so we will come back to it a little later when we discuss how the sun evolves. Okay, let me give a pictorial introduction to the sun. So there are two pictures shown here. One is on the left is the visible continuum, a picture taken from space, from observatory called Solar Dynamics Observatory. It's a NASA mission. It is a visible continuum at 4,500 angstrom. That's the wavelength of the light in which this picture is taken. This is a continuum visible light of the sun, which usually comes from a layer called photosphere. Okay, and you see a dark spot there. It's a sunspot. There's only one sunspot when this picture was taken. And on the right, you see a picture of the sun taken in ultraviolet at 1600 angstrom. It captures a layer called a chromosphere, slightly above the photosphere. It is taken at the same time. These two pictures are taken at the same time. So you see this somewhat inhomogeneous structure on the sun. The white light is more homogeneous except for the spot. But if you look at UV light, there are structures. The sunspot itself appears dark, but then surrounding that is, you see a lot of bright regions. These are called faculae or plages, which emit, as you can see in this picture, in UV wavelength. They are much brighter in UV. Okay, so we will again discuss this as we go on. And the sun is pervaded by a magnetic field. Okay, and all ranges of strengths and scales and shapes, as you can see in these pictures. There is a movie here. It is taken from real spacecraft observations from space, a sunspot region observed in various wavelengths. On the top here is the picture of a group of sunspots, and then the normal granulation which appears in small grainy popcorn-like structures. Okay, and the sunspot itself is very dark. It has a dark umbra and a penumbra. So what we know is sunspot is a strongly magnetized region, and the middle picture shows you a magnetogram. I will explain to you a little later how we measured this. It's a magnetic field of the sun that the dark and white patches, the black and white patches are the two polarities of the magnetic field. So wherever the field strength is very large, of the order of few thousand Gauss, then you see a dark area like a sunspot. And in this particular picture in the middle, in the magnetogram, you see a large number of regions which with two polarities in each region. These are called bipolar regions. Usually sunspot appears in the leading polarity of these regions. And if you look higher up in the atmosphere, you see these nice loop-like structures, which is taken in extreme ultraviolet wavelengths, again from space, which UV wavelengths you cannot observe on the ground. All right, so sun is a highly magnetized object. So one of the reasons why we study the solar interior is to understand how this magnetic field is generated. We believe that it is generated somewhere inside the sun. And that is one of the reasons we study the interior of the sun. Okay, so now let me also show you another picture where you might have all heard about a new telescope which was newly commissioned in the US. It's called the DKIST, Daniel K. Inouye Solar Telescope. It's a 4-meter solar telescope. It has taken the highest resolution pictures of the sun. On the right, you see a very close-up picture of this granulation, and then there are these bright, in between the granules. The granules are the bright structures, like popcorn, like bright, and they're surrounded by a dark lanes. Among these dark lanes, you see there's some bright structures. Those are actually magnetic fields, which makes the region little brighter, hotter, and it emits more light. So those are called the faculae. Let me play this impressive movie, real observation from DKIST, a very mesmerizing picture movie of the sun in very high resolution. So what you see is the bubbling gas. It's called granulation, and very, very high resolution, you see these tiny white structures, which are called faculae, as I just said. And their dynamics is very important to understand certain physics of the sun. We'll again come back to it. Okay, so these are all to motivate. Let me now start with give a slide showing the vital statistics of the sun. On the right is a cartoon picture of what we understand as the overall structure of the sun is. Its radius is 6,696 megameter. 696 lakh kilometer. Yeah, so it's about yeah. We also use a unit called megameter. 1 megameter is 10⁶ meters, or 1,000 kilometers. This will be 696,000 kilometers. Age is about 4.5 billion years. So I hope I am audible to everyone. So Satabtwa, if there is any problem in the internet, if you're not able to hear me, please alert me. Because I won't know in Zoom. That's the problem. Everybody is listening. Everybody is able to listen to me or not.
Sure. I'll let you know.
Okay, fine. So the age of the sun is about 4.5 billion years. Its mass is 2 × 10⁻30 kilograms. The sun is made of 73% hydrogen, about 24.8% helium, and all the rest, about less than 2%, around 2%, is all the other elements which we all made of. All right, so the sun's luminosity is about 3.8 × 10⁻26 watts, or joules per second. The central temperature in the sun at the core is about 15 million Kelvin. The surface temperature is about 5,800 Kelvin at the photosphere. And the corona, the outer layers, which is only, so this picture is only a kind of a cartoon depiction. I will later show some pictures of real pictures of corona. Or the next lecture will talk in detail about that. The corona is much hotter than the surface. The outer layers of the sun is much hotter. It's about 1 to 10 million degree Kelvin. It's called the coronal heating. It's kind of one of the not very well understood feature of the sun. How the corona gets heated to so high temperature is not very well understood, and it's part of active research. So let me explain a little more about this picture cartoon diagram. So what we believe is this: the core of the sun. So you see the core is where the nuclear reactions happen. Basically, hydrogen fuses into helium and generates all the energy. The photons which are emitted there, it takes about 10,000 years to come to the surface because the gas is so dense, the opacity is high. The photon takes a random walk to pass through the layers. So up to about 70% of the sun, up to, as you can, I hope you can follow my cursor, up to about 70% of the sun is like a solid body. It's called a radiative zone. The outer 30% is convecting. The slightly reddish color, the yellowish color is the radiative zone. And the outer 30%, which is shown in red, is the convective zone. So the paths which are shown in dark lines are these are the ray paths. What we call as the ray path are the paths of acoustic waves which travel inside the sun. Okay, so that is really later part of my talk, which I will cover. The P, what is denoted as P, is the acoustic waves, and what is denoted as G are gravity waves, internal gravity waves. So these lines show the paths of these waves inside the sun. Okay. Also, okay. So then photosphere has these granules, and then there are sunspots. Just above the photosphere is the region called chromosphere. And the chromosphere is highly structured, as you can see in this illustration. And then the corona. The corona is not uniform. There are streamers, which you can see during eclipses, and then prominences. And there are also regions where you don't see much streamers, not much material. Those are called coronal holes. Okay, so this is the kind of overall cartoon picture of the sun. So why do we, why understanding the interior of the sun is important? So,
hello, Rajguru.
Yeah.
Yeah, there are a couple of questions for you.
Okay.
So the first question is from Zubair. He's asking that, sir, do these stats vary with time? If yes, how fast they do?
Sorry, repeat the question.
He's asking, do these stats vary with time? If yes,
the statistics.
The statistics that you have talked about, do they vary with time?
If they vary, how fast? So okay, so it depends on what quantity you are interested in. Okay, the overall mass of the sun, of course, it varies a little bit, but compared to the total mass of the sun, the reduction in mass, there is a solar wind. There, as you can, you might have heard of, there are eruptions on the sun. There is a continuous flow of gas outward from the sun. It's called a solar wind. It slowly loses its mass. I don't remember the exact number, how much it is losing to solar wind, but it is for the overall dynamics of the sun, for the structure of the sun, it is negligible. Okay, and the radius also doesn't change much. It changes on an evolutionary time scale in billions of years, but not on human time scale. It is literally constant. And the composition, hydrogen or helium. So as I will discuss a little later, the hydrogen fuses, I told you, there is an initial, what is given is the initial composition of the sun when it was born. But hydrogen fuses into helium in the core. Okay, so the hydrogen fraction will slowly decrease over time, again on an evolutionary time scale, because hydrogen is converting to helium. So hydrogen will decrease, helium will increase at the core, but not in the outer layers. Only where the nuclear reactions happen, it will change. The luminosity again doesn't change. The central temperature, luminosity again, I mean, all these quantities do not change on millions of years. It takes billions of years to change. Okay. All right. I hope that answered your question.
Okay, and there is one more question for you.
Yeah.
A related question is that it's a question from Palini Muthu. He's asking, how do they find the core temperature of the sun?
Okay, so there are several ways to I will explain. Part of my talk is to model how, in a detailed way, how to model the interior structure of the sun from theoretically you can calculate. So the basic way to observationally, I mean, experimentally, you can measure again using helioseismology. I will again come to that. A simple way to estimate the central temperature is to assume balance between gas pressure and gravity. Okay. Yeah, if you just balance the pressure to gravity, if you know the mass of the sun, we can determine the mass of the sun through planetary motions. Okay, and then you can also determine the size of the sun from direct observations. Mass and size will give you, you can estimate the gravity, surface gravity, and then you can estimate how the gas pressure will balance against gravity. So, so that simple calculation will tell you this. Okay, I will little later, I will show you how exactly it comes about. And then we can observe, experimentally, you can verify the temperature, that is using helioseismology. Okay, I hope that answered the question.
Okay, and
so,
there's also one more question. Would you like to take it now?
Okay, quickly, yes.
Yeah, so it is a question from Rishabh Pandey, and he's asking, what is prominence?
What is a prominence? Prominent, okay, fine. I think the next lecture will cover, I am not talking much about the outer atmospheres of this sun. Piali Chatterjee, the next speaker, will cover in detail. In a simple way, a prominence is a loop of magnetic field, okay, out on the outer atmosphere of the sun. There is a magnetic flux. That you have seen the sunspots, right? The sunspot is intense magnetic field regions. There is a cylindrical flux tube which comes out. Within that, the field is very high, and it connects to an opposite polarity region in those two foot points, what we call. So in the magnetic field, since it has certain force, it can confine the plasma and it can hold it up there, like a levitating gas up there. So that is a prominence. Okay, how exactly it happens, it's dynamics of it. The next lecture will discuss to you. Okay. All right. Okay, let me move on. So let me give a little more justification or motivation for why we study the interior of the sun. So as I said, the sun has been shining for the last 4.5 billion years, almost kind of uniformly. And we know that its energy is coming from the nuclear furnace at the core. And then all this, sorry, let me play this video again. So this picture is called a coronagraph. It's a movie from space, from observation made from space. It shows the eruptions on the sun, okay, and which are all caused by this eruption of those prominences or solar flares. There is something called coronal mass ejections. All of that happens on the sun, which is, we believe that it is all contributed by or caused by the magnetic field. So the magnetic field is believed to be generated by a dynamo inside the sun. It's called the magnetic dynamo. And then the dynamo generates the magnetic field. The magnetic field emerges through the outer layers of the sun and causes all these explosive phenomena. Okay, and then it causes the space weather. Okay, so what you saw in just saw in the movie there, the huge explosions on the sun, which are thrown out of the sun, and sometimes it comes towards the Earth's direction, and they cause the weather in the near Earth space, and that is called the space weather. And space weather disrupts our human technological systems. In space, we depend on space for various things. The satellites which we launch for our communication, for defense, for science, all of that depends on, you know, the conditions there in space. And the conditions are highly variable, and the sun causes it. So we need to understand the interior of the sun to really understand and predict how that can happen. Okay, let me also quickly go through the basic tools we need to study the sun, not just the sun and stars, in fact, all the astronomical objects in general. To build a stellar model, you need thermodynamics, atomic physics, radiation theory, nuclear physics, and of course, hydrodynamics or fluid dynamics. The atomic physics, radiation, and nuclear physics are linked by quantum mechanics. So the microphysics governed by quantum mechanics plays a big role in the structure of sun and stars. Okay, and then of course, since the sun is a plasma, I mean it's a fully ionized gas. So then the motion of gas, and then we also saw that there is a strong magnetic field. There is a magnetic field generated inside the sun. So the behavior of plasma in a magnetic field is governed by a subject called magnetohydrodynamics. I will not go into detail of this subject, but again, purely in the next lecture we'll cover. And then observationally, we use multi-wavelength imaging and then spectroscopy, which imaging in the sense you take a picture of the sun in very high resolution using powerful telescopes in various wavelengths. And then you can build a spectrograph and then study the spectral lines, which you all know what a spectral line is. And then that examples are shown here. The subject is called spectroscopy. You split the light from the astronomical object into spectra, and then study the structure of the spectra, which you see. The spectra are basically absorption lines caused by elements on the emitting object. And then you can also do spectropolarimetry. That means you can also measure not just the intensity of light, you can also measure the polarization of the light in the so-called Stokes parameters, which define the polarization state of the light, which again you can build instruments to study the polarization. That's called spectropolarimetry. So these are the basic tools. And I just focus on two important effects which we very commonly use. The one is due to Zeeman, which you all might have studied in your BSc or MSc, the Zeeman effect. An emitting object, an atom which emits, when it is subject to a magnetic field, and the transition which makes the electrons, which transition from one level to another level, atomic levels in an atom, in the presence of magnetic field, they get split. Okay, so the lines which you see, absorption lines, usually get split, and that's called the Zeeman effect. So the Zeeman effect, the wavelength shift of these split due to Zeeman effect is proportional to the magnetic field strength, which and then it also depends on the wavelength, and there are other parameters called Landau G factor G, which determines it's atomic parameter, depends on, it characterizes different atoms, how sensitive they are to the splitting. Okay, so this is one of the important effects which we use to measure the magnetic field on the sun. Some of the pictures I showed you, the magnetograms are made by analyzing the light from the star, the spectral lines, and then measuring very accurately the Zeeman effect. It is, it was discovered by Zeeman in 1896. The real observations of the Zeeman effect in astronomical object, the very first astronomical measurement of Zeeman effect came in the early 20th century, 1908 or 1909. That's measured on the sun for sunspots. And then the other effect which was discovered earlier is called the Doppler effect. If the emitting medium is moving with respect to you, it produces the shift in wavelength. Okay, you can either write them. If the velocity of the source is not so high, if it is not relativistic, use the formula on the left. If it is relativistic, you see the other formula there in the right. So measuring the shift of the line is the Doppler shift. It was discovered by Christian Doppler in 1842. We use that very commonly to study the motions of astronomical objects. And okay, these two effects very commonly used in the sun. All right. Okay, so this is again a picture of, just I showed the very first observation of extraterrestrial magnetic field came from George Ellery Hale in 1908 in the US. He built a spectrograph to measure the Zeeman effect. And this is from his own original observation. There's a spectral line here on the right side of this plot. There's a sunspot, there's a slit. This is the slit of the spectrograph. If you disperse the light and then you plot in the x-axis is the wavelength. At the location of the sunspot, you see this broadening. Basically, the line is split into three parts. Okay, it's just like what I explained in the Zeeman effect before. So it was the very first observation by George Ellery Hale. Just around the same time in 1909, John Evershed was a British officer who was posted in India. He built, he was in Kodaikanal. The IIA, Indian Institute of Astrophysics, is originally called Kodaikanal Observatory. John Evershed was working there in Kodaikanal. So our IIA in Bangalore kind of evolved from the Kodaikanal Observatory in Kodaikanal. We still have the observatory there. So in 1909, John Evershed, he first observed the Doppler shifts of the spectral line on the sunspot. Okay, on the right here is the modern observation of a sunspot in continuum on the top, in magnetic field at the middle. This is called the magnetogram. So you basically observe the Zeeman effect and measure the Doppler the shift of the line due to Zeeman effect, and then you convert that into magnetic field, and then you plot in the color scale. Bright white structure is a positive magnetic field, and the black area is a negative magnetic field. Okay, and that's called the magnetogram. That's how we measure. On the bottom is the Dopplergram. So you measure the Doppler shift, and then plot. You can convert the Doppler shift into the velocity. And then again, the bright and dark regions are positive velocity and negative velocity, okay, with respect to u, with respect to the line of sight. So as you see at the location of the sunspot, there's a very strong magnetic field, but then there is also a very nice kind of a dipole-like structure. There's one side is bright and the other side is dark in the sunspot. So this is called the Evershed effect, which is discovered in Kodaikanal in IIA by John Evershed, okay. All right, so that is what we, okay, let me now jump to
Rajguru.
Yeah. Yes.
Yeah, there is a question for you.
Okay.
So the question is from Arya Datta Munshi, and the question is, how do we distinctly differentiate between the umbra and the penumbra?
How do we differentiate? Okay,
yes.
It depends on what quantity you want to use. If you take a nice picture, in a very high resolution picture of the sun, like what I showed earlier, you see a dark region, which is, as you can see here, for example, the dark region, much darker than the photosphere, is umbra, and then in between brightness, in between the quiet sun and the dark umbra is this penumbra. Okay, you can differentiate using intensity, how bright they are. You can put a cutoff. Or you can also use magnetic fields. Okay, so in terms of magnetic fields, the umbra is mostly vertical magnetic field. If you make a very detailed analysis of Zeeman effect, you observe more or less vertical field causes this darkening, and then slightly bent horizontal field which expand and bend like this, and those define the penumbra. In the penumbra, basically the magnetic fields are more or less horizontal. Okay, so yeah, so that's how you can differentiate umbra and a penumbra. But there is, in principle, there is no hardcore, highly quantitative number you can quote for an umbra and a penumbra in terms of magnetic field or intensities. But there is a smooth transition from umbra to penumbra. Okay, maybe not so smooth, but you can clearly identify a boundary, dark boundary to the umbra. If you use a threshold, typically what we do is about 0.7 times the quiet sun intensity kind of defines the umbral boundary. Okay, and yeah, okay, does that answer? Okay, Sadatwa, can I go ahead?
Yeah, we can go ahead now.
Okay.
Yeah.
So let me now jump to the main part of this lecture, which is I want to describe to you how we model the interior of the sun. There are some equations, some differential equation. I understand that most of MSc syllabus in colleges, in the university syllabus, doesn't have fluid dynamics. Okay, so you might not have come across these equations, but I will. But then the basic principles we use, the basic physical principles, you must be you are already familiar with. So don't worry much about the equations. But the basic equations are the physical principles which we use to model the interior of this sun or star is are the three conservation laws: mass conservation, momentum conservation, and energy conservation. That's what I have written here. if you write them as a differential equation, so since we are not dealing with mechanics of discrete objects, this is a gas. Sun is made of, or sun and stars are made of, it's in a fluid state, it's a gas. So we typically use hydrodynamic equations. Okay, so that is what is shown here. Okay, there is a slight distinction between hydrodynamics and fluid dynamics. Let me just make that distinction here. So that is by whether you include viscosity or viscous or friction forces in the momentum conservation or not. If you don't have viscosity, it is called hydrodynamics. If you put viscosity, okay, viscous forces, basically force due to friction or viscosity of the plasma or the gas. If you include that, it is technically called fluid dynamics. Okay, those are called Navier-Stokes equation. But generally, we use hydrodynamic equations to study the sun and stars because the viscous forces are largely negligible. They don't contribute much. Okay, so with that distinction, let me just explain to you what mass conservation is. The mass conservation, as you all know, the given amount of mass has to be conserved. So in a differential equation form, you can write that as this equation. Rho is the mass density, and these different variables are rho is the density, v is the velocity of the plasma, and the other quantities are p is the pressure, okay, and then f is the energy flux, and q is the heat energy per unit mass. Okay, there are other quantities here in the energy conservation. Let me come one by one. So this mass conservation. So generally, when we these are the three equations which we write down for these three conserved quantities: mass, momentum, and energy. All right. Okay, so these are as you can notice that in every equation we have this velocity, that is velocity of the plasma or the gas we are dealing with. So fundamental assumption we make in applying these equations to sun or star is that we assume the property change very slow. Okay, so the gas is static. Okay, in reality, this is not true. As you can see that in the beginning, some of the pictures I showed you, there are these violent eruptions, convection, everything going on the sun. But it turns out that much of the interior of the sun is static. Okay, the outer layers which participate in motions, okay, they contain very little mass. In terms of mass, the outer regions are composed of very little mass. More than 98% of the mass is in the radiative zone. So it is static. So the assumption of neglecting the velocity and time rate of change of quantities, time rate of change of all these quantities is very well justified. So we neglect time rate of change of these quantities, the d by dt in these equations. So the first equation is d rho by dt, the mass density, how it changes is related to how the mass moves, right? So that's a conservation of mass. So if you neglect the velocity and the time rate of change, it basically only this divergence of rho v, the v is also equal to 0. So you can convert that into this equation. dm by dr is equal to 4 pi r squared rho. The rate of change of mass, this m is the function of radius. R is the radial coordinate. You define a radial coordinate from the center to the outside. R equal to 0 is at the sun center, and basically spherical coordinates. And dm by r, m is the mass coordinate, mass contained within a radius r. dm by r equal to 4 pi r squared into rho, mass density. Okay, the density is just the mass per unit volume. Okay, so this is what you get for mass conservation. In the momentum conservation, basically mass into acceleration, that is what is rho into dv by dt. Mass into acceleration, which is basically for the gas, continuum gas, it is density into acceleration, dv by dt. And in fluid dynamics, there is a partial derivative of velocity, as well as this called the advection term, or the v dot grad v, the spatial derivative. So the whole thing determines this acceleration. partial dv by dt plus b dot grad v is the actual total acceleration of a fluid particle times the density, that is mass per unit volume, is the force. So the force is equal to pressure force. Pressure force is the force due to pressure is the gradient of pressure. Okay, and the spatial gradient, spatial derivative of pressure gives you the pressure force. And then of course the other term is the gravity force, which is g is acceleration due to gravity. The gravity force is m times mass for an object. The gravity force is mass into the acceleration due to gravity. For a fluid, it will be rho times g. Okay, so basically we balance the pressure and the gravity to the acceleration of that fluid particle. Now we assume that the fluid particle is not really moving. So that means that the pressure force grad p just balances the gravity. Okay, so that you can write down like this in the middle down here. dp by dr is g times rho. G is acceleration due to gravity is gravitational constant times the mass divided by r squared. This is your acceleration due to gravity. Okay, so this is one of the fundamental principles. The stars are self-gravitating bodies in dynamical equilibrium. So gravity just balances the internal pressure force. Okay, and the energy conservation is you have to conserve the energy. So you define a quantity called heat energy per unit mass, and the rate of change of that is equal to how much is generated, mass times the nuclear energy generation rate, this epsilon here, minus how much of the energy is going out. Okay, divergence of the flux of energy flux. And epsilon, this E is nuclear energy generation rate per unit mass. Okay, so this is the energy conservation. Again, if you assume it is very static, okay, overall there's no net heat gain or loss, then if there is a uniform flow of energy everywhere, so then you can energy balance, you can neglect the time derivative, just by equate the energy generation rate on the right to the luminosity. Divergence of F you can write as a derivative of luminosity. This flux, F is flux, luminosity is integrate over the area. Okay, so this is the third equation. Okay, so let us not go into much more detail. So these are the basic principles which we use, and the reduction of this hydrodynamic equations for the static case leads into this the so-called stellar structure equation. So there are mass conservation, the momentum balance, gas pressure balances the gravity, and the energy generation inside the core balances the energy going out, the luminosity of the star. Okay, there are other terms which we will not go into the complications of that in this lecture. So you can also you have to model while trying to build the model using this equation. You need to consider how the energy is transported. Okay, so there are two major mechanisms of energy transport. One is called radiative diffusion, which is energy transported by radiation. And also on some regions of the star, as I told you, in the outer 30% is convecting. So you also need to model how the energy is transported by convection. Okay, so those are very, very severe difficulties in modeling. So the convection, for example, is very difficult to model. So we only model in a very phenomenological way. Okay, so we will not go into the details of that. So and then while modeling the radiative transfer, we also need to take into account a quantity called opacity. So that it means that basically describes how the radiation interacts with the matter. So the energy, the photons which are generated at the core of the sun, they have to diffuse out. Okay, they have to travel outward. While doing so, they interact with the atoms, with the material, matter. So that interaction of photons with the matter is controlled by a quantity called opacity. This is basically, it's called mass absorption coefficient. Okay, again, it involves calculating how photons interact with matter, requires all atomic physics. Okay, so we typically use this as the input. So atomic physicist will give you, if you have a certain temperature and certain composition inside the sun, thermal quantities, they will give you how much will be the opacity. Okay, we use that as an input. And then this E, nuclear energy generation rate, again depends on nuclear physics. So there is a, yeah, I think that is all what I have in the, okay. Let me,
hello.
Yeah.
Yeah, again, there are a couple of questions.
Okay.
So the first question is
Yeah.
from Prasad Rathod.
Yes.
Does the mass conservation law violate when it comes down to coronal ejection?
Yes, in a static condition, if you assume it is, if you don't include the time variation, yes, you violate the mass conservation because some mass is going out. But as I told you, it is very negligible. For the overall mass of the sun, the rate at which the mass is lost due to eruptions or solar wind is very, very tiny. And the effect of that is usually not modeled in a, I mean, there are models which you can take into account mass loss. But what I described right now, the standard way of building a stellar model ignores that. Okay. I hope I answered that.
Okay,
so it is a very good
question.
assumption to ignore that for the sun. I mean, for stars in the main sequence, in the main lifetime of the star, I mean, low mass stars, it is a very good assumption to neglect the mass loss while building an interior model of a star.
Okay, and there is another related question.
Yeah.
This is from Palani Muthu, and the question is, do all the stars have same mass? If not, then how can we find the mass of a star?
Oh, okay. That's a very interesting question. So, no, of course not. So, as I told you in the beginning, there are stars of various masses, right? So, typically, there are very simple observational ways to determine the mass, but I mean, indirect ways, but there are very difficult to get a very accurate estimate of masses of stars. So, if there is a binary star, if there is one star is moving around the other, then by measuring the period of this in some way, if you can determine spectroscopically, then you can, using Kepler's laws, you can relate to the mass and determine the mass. So generally, it is very difficult to determine the mass of the star other than the sun. There are other theoretical modeling which you can do through other quantities indirectly. Yeah, I will not be able to explain that in this particular lecture, but there are ways to determine the mass. One is the way using binary stars, or if you have a system, if you can resolve the planets around stars. I mean, these days we do measure exoplanets around stars. That way you can also determine, if you can determine the orbits of these planets, or the orbital period, you can again determine the mass of the star. Yeah.
Okay, and sir, one more question is there for you.
Yeah.
So this question is from Sri Bala, and the question is, why solar mass is used as a reference for stellar masses? Is there any other stellar mass used likewise?
No, we use the solar mass because sun's mass is very well determined. It's a very accurate number we have for the sun. So that's why we use in solar masses all the other astronomical objects. And also sun is our closest star. We study that very well. I mean, it is, you can see if when people studying galaxies or in cosmology, they don't use, I don't think they use mass in unit of solar mass. But typically in astronomy, generally we use mass unit as the mass of the sun because it's very well measured. Okay, shall I go on?
Yeah, but I mean, some questions are still popping up, but we are running short of
Okay,
time.
I think we are running late. So we will kind of defer the questions to the end. Is that okay?
Yeah, I think
okay.
that's
There is a lot more to cover. Sorry, I am going a little slow, I think. Okay, I will go quickly. So let me, okay, so I explained to you the basic equation which you use to model the stellar structure. And then we also need to make some assumptions about our empirical quantity to start with, what is the sun is composed of. Okay, this we measure from various measurements. Spectroscopically, we can measure what sun is composed of, at least in the photosphere. So you can determine how much of hydrogen is there, helium is there, and all the other metals are there. So the photospheric abundance is taken as the abundance when the sun also formed. Okay, so we typically denote hydrogen as X, helium abundance as Y, and all the other elements as Z. Okay, so this goes as an input. I will skip this. So how we determine cosmologically using other observations also discussed here. I will skip this. The other basic inputs is called, there are three basic other inputs. One is called the equation of state, which relates the three thermodynamic quantities. We generally use the ideal gas equation of state, P equal R rho T divided by mu, mean molecular weight is mu. And in terms of the abundances of three species, mu is given like this. And then, of course, these nuclear reactions. I will not go into describing the nuclear physics involved. What we understand is that the proton-proton chain, that is the hydrogen nucleus and hydrogen nucleus colliding and form a helium. It is not in one go. There is a set of reactions involved in the PP chain, which is happening in the core. So this comes from nuclear physics. Okay, the stellar modelers or solar modelers themselves don't do nuclear physics as such. We given the thermal conditions in the star, the nuclear physicists will give you the chain of reactions and their rates. Okay, and that determines how much energy is generated inside the core. And then, of course, I told you about opacities. This comes from atomic physics, again, nuclear atomic physics calculations, which involves quantum mechanics. Okay, all right. So there are also other nuclear reactions called CNO. But for sun-like stars, we believe that most of the nuclear energy comes from this PP chain on the left. So this plot shows the logarithmic units in y-axis, how much of energy generated due to nuclear reactions. And then as a function of temperature in millions of degree Kelvin. So the blue curve is for PP. So the sun's temperature is around, core temperature is about 15 million Kelvin. Since it is log unit, you can see that the contribution due to PP chain is much, much larger than due to CNO. But the CNO dominates when you go to much, much hotter interiors. If you go to more massive stars, and the stars in core temperature is much, much higher, they dominate, they produce their energy due to CNO cycle, where again, hydrogen fuses, a net product is helium is produced, but through the catalysis produced by carbon, nitrogen, and oxygen. Okay, I will not again describe the details of those. Okay, so once you have these inputs, you can build a series of models. Okay, then you can solve those equations and then follow the slow evolution of the sun as a star. So what is plotted here is the solutions of those, what I just talked about, as a function of solar age, scaled by all the quantities which are today. So whatever quantities plotted here, you divide them by the values of them for today, and then you plot them as a function of the age of the sun. So you can see that the temperature is slowly increasing, the core temperature. Okay, what is plotted in this left diagram is with the subscript C, stands for core. So for example, the hydrogen keeps falling down. Okay, when it started, hydrogen was certain fraction, and it keeps falling down because hydrogen is converting into helium. So the X hydrogen fraction keeps falling down, and this is today's value. Okay, and then similarly for other quantities, we can plot the central temperatures, central temperature and central density and pressure and all this. Okay, and then you can, on the one important quantity which you can plot is the luminosity of the sun as a function of its age. So today, let us call it as one solar luminosity. Okay, but if the black curve is as a function of age, you see, divided by the current luminosity, you see that when the sun started, when its sun became as a star, it was only 70% as luminous as today. That means it was 30% darker than today. Okay, so this is called the faint early sun problem. Okay, so if from what we know, the Earth has been there as long as the sun is, and if the sun was only 70% as bright as it was today, So we expect that to start with, the Earth would have been completely frozen when it was born, Earth, along with the sun. But what we know is that it is not so. That's called the faint early sun problem. It is not fully resolved. How come Earth, maintain its maintain its environment without completely being frozen? We know paleological record, Earth's paleo records show that Earth was not so frozen in the past. There are some ice ages which come and go, but not completely frozen when it was born. So that is called the faint early sun problem. Okay. So Sadato, how much time we have? Another half an hour?
No, you have around, let's say 26 minutes.
All right. Okay. Nearly half an hour. Okay, fine.
Yeah.
Let me go quickly. So this what? So then based on those description I produced, then you can make a standard solar model. Okay. So this is the picture again, I already explained to you. If you do the solutions of those equations and make a kind of a graphical picture of the structure inside the star, this is how it looks. Okay, nuclear energy is generated inside the core within about 0.2 solar radius, and then the radiation diffuses out. The matter doesn't move. At a particular location, it moves. So I didn't go into the detail how you determine when it starts to move. So what you can do is, once you solve the equation, you can find the temperature gradients. If the temperature gradient as a function of radius is greater than certain value, which is called the adiabatic gradient. That's called the Schwarzschild criterion, which somebody else will teach you later. So that will be violated. So if the gradient of the temperature is not smaller than a particular value, then the energy cannot be transported by radiation. Then the matter should move. And we find that exceeding, it's called the Schwarzschild criterion, the temperature gradient exceeding the adiabatic gradient happens at about 0.7 solar radius. That is plotted here with the outer layer is basically convecting. Okay, the energy is transported by convection. Okay, so this is a standard model. So you can plot the various quantities. Here I have plotted the temperature inside in logarithmic units inside the sun as a function of in radius units. Surface is 1 solar radius, core is 0. So this is how the temperature increases. Like that, you can plot various other quantities by solving those equations with all the inputs I described. Okay, I will go through this now quickly. Okay, so now once you do that, now what is the difference in structures? The structure I described to you in the middle. Okay, for 1 solar mass. So by doing the same analysis, same modeling as I just described to you, you can also solve those equations for different masses of the stars. It turns out that if you take a very high mass star, more than 2 times the mass of the sun, the structure looks different. Okay, the core is convecting where the nuclear reactions happen. The plasma is moving, convecting at the core, and then the outer layers are radiative. They don't move. This is in high massive stars. And if you go to that means they are hotter also. They are blue means hotter than the sun. Red, sun is yellow, red is cooler than the sun. And if you go to smaller mass than the sun, and they are cooler, and they are called K or M dwarfs. And it turns out that almost all the interior is convecting. Okay, so these are differences in stellar structure you will get while solving this stellar structure equations. Okay. Now, so far I talked about the static structure, but sun is also moving in the sense that it has the large scale rotation, differential rotation, and something called meridional circulation. So these are all considered as small perturbations in the structure of a star. Okay, both the rotation as well as this, there is a meridional circulation inside the star. There is this plasma, a river of plasma going from the equator to the poles, and then sinks in the poles, and then goes down to the base of the convective zone, and then again comes up. So this is called meridional circulation, which we know it is happening by observation at the surface, but we don't know the interior structure. And then there is this differential rotation. The rotation is about 2 kilometers per second at the surface. And as you go towards the pole, it is rotating slower and slower. In terms of rotation period, which you all know, sun's rotation period is, the mean rotation period is about 27 days, but the equator rotates at 25 days and the pole takes about 30 days. That's a differential rotation. So this differential rotation happens in the outer 30% of the sun. Okay, I will skip this. So now let me describe to you a little bit in the remaining time about helioseismology. So how do we test the models which we build, the solar model or any stellar model we build? You have to verify the theory. So that came from helioseismology for the sun. The standard solar model which I just described, you can experimentally verify using helioseismology. Okay, so the discovery of the so-called 5-minute oscillations. So what you see as the movie here is the real Doppler observations of the sun. I already explained to you what Doppler effect is. You can continuously observe the sun in Doppler, and you make a Dopplergram and make it as a movie. This is made by a spacecraft, an instrument called MDI on SOHO. After processing the data, what I play as an animation is what you see as the flicker is actually the solar oscillations. Okay, so this is a modern observation as an animation. So the flicker is what you see in the middle. You see slightly larger vibration than towards the limb. So that is because of our viewing angle. I mean, the line of sight, the solar oscillations are mostly vertical. So that means towards the limb, it is vertical to the sun surface. So towards the limb, they will go out of your line of sight. So that is why you don't see the this oscillations are towards the limb very well. But anyway, so these were very first observed by Bob Lycan, Noyes, and Simon, these three gentlemen in California in 1962. Bob Lycan is the one which you will see in the Feynman lecture series, Feynman and Lycan lecture series. He was a colleague of Feynman. He was interested in studying the sun. Basically, he built an instrument to study the convection on the sun. In the course of that, he discovered the sun is vibrating in 5 minutes of period. These vibrations are 5 minutes. The typical period is 5 minutes. And the gentleman on the right, immediately after this discovery, a few years after that, they explained this observation as oscillations trapped inside the sun. So that is the animation which you see on the right. So these are the ray paths of these acoustic waves inside the sun, which get trapped inside. It's vibrating like a resonant ball, like a spherical ball, which is vibrating. So the simple physics involved is that I have explained in these slides. If you take a guitar string and if you pluck it, you have this normal modes of vibrations in 1D, and in 2D is this vibration of a drum. Okay, so these can also be described by simple wave equations, I assume, which you all know, which I have described here in this slide. And similarly, in 3D, a 3D object will vibrate as a whole as illustrated here. Okay, these are very exaggerated diagram showing the solar oscillation vibrations of the sphere, but in reality, the sun vibrates in a very, very small amplitude. Okay, all right. Okay, so I will skip this. So the same basic equation I showed you to start with, you can build a theory of these oscillations by perturbing those equations. These are linear analysis, perturbation analysis. Okay, if you just take it for granted that there are well-developed ways to model these oscillations, and you can. So in the interest of time, I won't be able to go into the details of this. This is a simple mathematical process of taking those conservation laws and you perturb them each quantity for small vibrations, and assume that the vibrations are very small, and those vibrations are denoted by quantities with prime. All the physical quantities with the prime are those small perturbations, small vibration. You assume them to be small, and you put them in those equations and linearize them. So the basic equations, as you know, that basic hydrodynamic or fluid dynamic equations are nonlinear. So to study these oscillations, these small amplitude oscillations, you can linearize them. So you neglect all the powers of 2 and higher. So then you will end up in a simple wave equation for the sun. So that is what is shown here on the top. The psi quantity, psi r, is the the displacement of the sun's surface or the gas anywhere inside the sun. How it vibrates is given by this equation. So the time derivative on the right side has been converted into exponential time derivative, assuming that the perturbations are wave-like. Okay, so basically the message I wanted to give you is here that the whole sun can be treated as a vibrating spherical object, and you can write down a simple wave equation simplified from the original nonlinear equations, and you can study the vibrations of the sphere. Okay, all right, I will skip this. You can do this analysis, and let me again, in the interest of time, you will probably in the tutorial session, I will explain to you what the details of all this, and there is also exercise given how to model the ray path, the resonant wave which is inside the sun, how to model it. We will again come in the afternoon tutorial session. Okay, so what you can now do is you can solve that wave equation, and you plot the frequencies of these waves in y-axis and the wave number. This is since we are dealing with a spherical object, so there is a wave number called spherical harmonic degree, which you are familiar with. If you are familiar with spherical harmonics, you can you have this wave number called L, spherical harmonics. If you plot the frequencies of those waves as a function of spherical harmonics, this is the structure you see. Okay, there are these very discrete modes of oscillation inside the sun. Just like your guitar in 1D, if you attach at the two ends, if you pluck it, it vibrates in discrete frequencies. And similarly, a 3D object, like a 3D sun, the sun, spherical sun, vibrates in its discrete modes of oscillations. Okay, so those are basically acoustic vibrations, and those are called P modes. Okay, so the P modes are denoted, I have written there in this diagram. So the frequencies are, as you can see, these are in microhertz. Okay, about 3000 microhertz or 3 millihertz, which somewhere falls here in my, if you follow my cursor, that corresponds to 5 minutes. Okay, so there are these 5-minute oscillations as a function of wave number. And the other different lines, these are called ridges. The different ridges are called, they are denoted by these numbers here, starting with 0, 1, 2, 3, like that. These are the radial quantum numbers. So, okay, when you deal with a quantization of oscillations in a spherical object, just like what you do in your hydrogen atom problem when you do quantum mechanics. So there are these discrete quantum numbers. Radial quantum number, which is denoted as n, that is what is shown here. These different ridges correspond to this different radial quantum number. Okay, so those are basically related to what is plotted on the right is called the eigenfunctions. Okay, on the left is the eigenvalues. So the whole problem, wave equation problem, what I described is an eigenvalue problem. These frequencies are eigenvalues, and the actual perturbations in various quantities, if you take density or the perturbations, they are called eigenfunctions. If you plot the eigenfunction as a function of radius inside the star, that's how they look. The number of times they cross the 0, okay, for the wave function, they are the numbers which are these radial quantum numbers. Okay, all right. Okay, so this is the basic description of the solar oscillations. So now the task, so they are all determined by those coefficients in those equations, basically the basic structure of the sun, the density, pressure, the gravity, and then there is something called gamma 1 adiabatic index, which comes through the equation of state. It's basically the ratio of specific heats. All these quantities which are inside the sun, they determine the properties of this oscillation, which are shown in this diagram. Okay, so that means if you are able to measure these frequencies, then you basically have a constraint on the interior structure. Okay, so how do we do helioseismology? This is through the Doppler shift. You observe the sun in a Doppler shift. Okay, you observe a spectral line which is formed at the photosphere, sun's photosphere. For example, you take one particular line in the Fraunhofer line, which forms on the sun's surface, photosphere. You follow in time in a spatially resolved manner. Okay, you follow that particular spectral line in time, how it keeps shifting. So if the sun is vibrating due to these oscillations, this line also will be vibrating, spectral line. Okay, so you measure the blue shift and the red shift, you can combine that into a Doppler shift. Okay, and then you can make a Dopplergram, which you see on the right is the Dopplergram of the sun. Okay, what you immediately see is, as you can easily understand, there is a dipole-like structure you see, dark on one side and bright on the other side. So that's basically because the Doppler, the line of sight motion of the sun, is dominated by its rotation. So one side is coming towards you on the left, and the other side is going away from you. So it's about -2 kilometers per second to +2 kilometers. Yeah, hello? Okay. Anyway, I heard some voice there.
No, that was from the recording place from IIA.
Okay, fine, all right. Okay, so when you make a Dopplergram, if you take a single Dopplergram, it looks like this. You mostly see the rotation, and then there are these other grainy structures which are due to convection. Now, if you take a single Dopplergram, and then since you measure it, so typically we make a Dopplergram. Typically, we make a Dopplergram every 1 minute or so. So I told you the solar oscillations are 5 minutes. So if you measure them in 1 minute or less cadence, then you will be able to sample the oscillations well. Okay, so typically we make an observation every 1 minute. You make a picture of the sun in Doppler like this every 1 minute. And then you take a time series of Dopplergram. You take, say, let us say you average for 45 minutes. Okay, and then you subtract it from each Dopplergram. Okay, that means that all the structures which live longer than half an hour or 45 minutes get subtracted out. Then the remaining perturbation which you see is the solar oscillations. Okay, so these are the basic data which we use.
So okay, you have around 10 more minutes.
Fine. Okay, I will finish in 10 minutes. Okay, so then these are the observational facilities which we have to observe the sun in Doppler. There's a ground-based network called GONG, Global Oscillation Network Group. Okay, there are 6 telescopes distributed all over the globe so that you can continuously watch the sun. Okay, so one of them is in Udaipur in India. Okay, so this is run by the National Solar Observatory of the US. It's a ground-based network of telescope which observe the Doppler shift of a particular photospheric spectral line on the sun continuously every 1 minute and makes a series of Dopplergrams to study the solar oscillations. And there are these other space-based instruments which we use. One is on SOHO. SOHO is a solar heliospheric observatory which was launched quite some time ago in 1996. But after that, this was NASA mission, NASA and ESA mission. There was an instrument called MDI, Michelson Doppler Imager, which measures the solar oscillation. And then now we have, from 2010 onwards, there is a new space mission which was launched by NASA again. It's called Solar Dynamics Observatory. There we have this helioseismic and magnetic imager called HMI. And these two spaceborne instruments have produced a lot of data. They have basically revolutionized our understanding of the sun. So both these instruments are from Stanford University. The solar group at Stanford University built this MDA as well as HMI. And HMI is now continuously making observations. Okay, so I already described to you the theory behind it. Now, if you take these observations and you take a spherical harmonic transform of these observations in space, I mean, R and theta coordinates, R, theta, and phi coordinate, you take a spherical harmonic transform. And then in time coordinate, you take the temporal Fourier transform and take a power spectrum. Okay, and that is what you see directly below this graph, directly below this picture is denoted as global. If you take a spherical harmonic transform and temporal Fourier transform and take the power spectrum of the oscillations, you will get a very nice picture of this observed spectrum of the sun. You have to compare this with the theory which I just showed you earlier. Okay, I will, this is called the global helioseismology. You take the whole sun's observation, convert that into a frequency wave number diagram. That's called global helioseismology. You can also analyze these oscillations locally, like shown in this animation. Okay, you can, instead of taking a spherical sun, you can take a small area and then you can do a local analysis. It's called local helioseismology. It's basically taking a sonogram of the sun. So very similar to directly take the space and time. Instead of taking Fourier transforms and spherical harmonic transform, what you do is you directly correlate points on this movie in a small region, points separated by a distance, you cross correlate them, and then you plot the distance versus time cross correlation. This is called the time distance diagram. This is basically a seismogram. So you can, just like seismology, you study waves by observing earthquake, waves produced by earthquake between receivers located at different places. Here in the sun, we have seismograms all over the surface. Each and every pixel here is a like a seismometer. And you can correlate and then find time distance. Is called the sonograms or a seismogram. You can also use that to study structures locally. Okay, we will again discuss this in the afternoon tutorial session, how to do this. Okay, now the task is to compare the theory which I showed you earlier with the observations on the right. Okay, what you do is the main principle of helioseismology is involved with comparing the theory on the left with what observation on the right, and minimize the differences between the theory and observations. So that way you constrain the basic structure of the sun. So if it is not matching with what you observe, then you tweak the model and make it match with the observations. So that way you tune your model. So that is the essence of helioseismology. So that's what we do. And again, we will come back to this later. So the minimization process is called the inversions, helioseismic inversions. Okay, so there are these frequencies which you can measure on the left side of these equations. This omega is 2 pi times mu, which is this nu here. You can measure them by fitting this observed spectra, and you can relate to them. You basically you apply this variational principles. There is certain models involved in determining these frequencies. Now you determine what should be the change in the model to determine the change in the frequencies. So on the left side is you start with a certain model and you take your observation and find the differences, and how the differences is related to the interior structure of the sun is given on the right side. It's an integral equation. It's a well-developed technique, helioseismic inversion we can do. So the left side is known. You want to find the unknown on the right. And the unknowns are perturbations in these models. Okay. And that is what helioseismology does. And that is the results are given here. Basically, the sound speed squared, for example, is plotted. Sound speed is related to temperature. Square root of temperature is sound speed. Or sound speed square is just directly related to the temperature. And you can find the difference between your observations and your model. So you can see these numbers are very, very small. As you can see on the y-axis, the difference between your model and the real sun as you observe from the solar oscillations. So these are the accuracies of the order of 10 power minus 3 or 10 power minus 4, right? The differences between your model and observation. So this is considered as a big achievement. So in astronomy, you don't get this kind of accuracy very easily. So we basically determine the interior structure of the sun. In this case, the sound speed inside the sun, which is related to the temperature or the pressure and the ratio of pressure and density and square root of that, is determined very accurately, right? And you can also determine the density. All right. Okay. So this is the essence of helioseismology. And you can also determine the rotation, assuming that this rotation, moving plasma, produces a shift in the frequency, just like your Doppler shift of the light. The Doppler shift of the acoustic waves also can be measured. Okay, if a wave is, if the medium in which the wave is propagating, which is the sun, if it is rotating, then you can determine how it will change the frequencies of those waves, acoustic waves which propagate through the sun. Okay, so that's the basic essence. So you can determine waves which propagate in the same direction as the rotation, and those waves which propagate in the opposite direction of the rotation. Using that information, this is called the rotational splitting of oscillation frequencies, which are related to the rotation rate. One can determine the interior rotation of the sun also. Okay, so that is what is graphically shown here. Red is faster rotating, blue is slower rotating. So you can, through this technique, we can measure the interior rotation of the sun. So as you can see, the equator rotates faster and the poles rotate slower, but it is changing as a function of depth, and the radiative interior below about 0.7, it is rotating almost more or less red, almost like a solid body. So there is a latitudinal differential rotation here, right? As a function of latitude, it changes from red to blue, yellow, and blue. That is those cuts are shown on the right for different latitudes, right? This is the rotation rate. Higher rotation rate means shorter rotation period. So the equator rotates the fast on 60 degree. We can't go up to the pole. Even though this diagram on the left shows up to the pole, we don't have real measurement. It's just an extrapolated color which is plotted there. We can go up to 60 or 70 degree. So the poles rotate slower. But what you see here is that at the base of the convective zone at about 0.7, the rotation rate comes down, the faster rotation comes down to a particular value, and the slower rotating poles increase to this particular value. So the interior is rotating as a solid body, whereas the different latitudes rotate differently. So you have a strong shear in this location at about 0.7 solar radius, right, as a function of depth and also as a function of latitude. So this is called the shear layer. It's called the Tycho line. So this was discovered and confirmed by helioseismology. Okay. All right. So the rest of this, I will stop here. And the rest of the helioseismology analysis, we will discuss it as kind of a tutorial session in the afternoon. Okay, I will take any questions now, Satapto.
Okay, so maybe we can take a few questions from YouTube.
Yeah.
So the question is by Hamish Delvadia, and the question is, are MHD waves responsible for high temperature of corona?
Oh, okay. So yeah, I didn't talk about that. I think Piyali Chatterjee will talk about that. I mostly focused on the solar interior. Yes. So what I talked about so far is the acoustic waves which live inside the sun. And as I told you, that there is a magnetic field which pervades throughout the outer layers of the sun in various structures, sunspots, and then there is small scale fields. There are prominences. All of that is controlled by the magnetic field. And they do support waves. Since it is magnetized completely, there are MHD waves, magnetohydrodynamic waves. And they are treated, they are considered as one of the agents for heating of the corona. I think Piyali will talk about that in detail, the next talk in the afternoon.
Okay, so there is another question by Haripriya Harikumar. The question is, how does the dynamics of solar corona related with sunspot cycle?
Sorry, dynamics of the
solar corona related with sunspot cycle.
Oh, okay. All right. Okay. So the sunspot cycle causes the dynamic corona, not, the corona doesn't cause the sunspot cycle. The sunspot cycle, which I will describe to you in little more detail. Because of the time, I didn't. Okay, let me show you a picture of that. Let me, 1 second. So. I did have okay, anyway, so you see this picture. So this is the sunspot cycle. Okay, what you see here is the so-called butterfly diagram. Okay, so if you plot as a function of time in x-axis and latitude, I think again Piyali Chatterjee will describe to you in detail. These are called sunspot cycles. So the number of sunspot, what is plotted here is sunspot area on the sun. It varies like this, and as a function of time, simply the area you plot in the bottom curve you see. Okay, so this is due to the dynamo which is operating inside the sun. Okay, So the dynamo generates the magnetic fields and they appear as sunspots. The number of sunspots grow in number every 11 years. And because of this particular feature of the dynamo, or how the sun's magnetic field varies, the corona is similarly changing. So that means in the sense that the number of eruptions or a number of prominences and all the other coronal structures also vary in response to this. Okay, so Piali again will discuss that in detail. Let me show you this movie. What we believe is as happening inside the sun as an animation. So the sunspots appearing. So this is a cartoon depiction of what we understand, but there's no full theoretical understanding of how the sun generates its magnetic field. What we believe is happening is like this: the sun's rotation, differential rotation, winds up this magnetic field inside the sun, and it causes these sunspots. And the previous movie, as it shows, you see on the right also. You see the sunspot number on the right, which goes up as a function of time as the field intensifies and sunspots are more produced, and then comes down again. So this happens every 11 years. Okay, I think I gave probably an extended answer to that question. Yeah, next question.
Okay. So I think there are questions on CMEs and corona. I guess Pialima will talk on those. So we can ignore them maybe.
Yeah, if there is anything else related to interior structure or the physics of oscillations.
Yeah, so there is a question by Naman Joshi, and the question is, can you shed some more light on acoustic and gravitational waves in sun?
Acoustic and gravitational waves. Okay, so it is not gravitational waves. Okay, let me use this diagram. So what is denoted as G modes is, so okay, there is a difference between gravitational waves and gravity waves. Okay, so gravitational waves are different. Okay, they are in general relativity. Okay, that is for the space-time. Okay, and the space-time itself fluctuates as a wave. That is called gravitational wave. But what is denoted here as G modes are internal gravity waves. So I didn't talk about much because we don't normally use them in helioseismology. These gravity modes are the restoring forces due to gravity, the buoyancy due to gravity, right? If there is a less dense plasma inside the sun, it will try to rise up due to the buoyancy force, right? Just like a water bubble rises up. An air bubble inside the water, because of buoyancy, it rises up. So similarly, if there is a low dense region appears inside the sun somewhere, it will try to vibrate, it will try to rise up. Okay, but then if that low density, the amount of perturbation in density is not too large, then it will vibrate as a wave. This density perturbation will propagate as a wave. These are the restoring force is the buoyancy force. So those are called gravity waves. Okay, these are, which you can see them in atmosphere, in Earth's atmosphere also. Sometimes you see this very nicely aligned cloud structure, like thin stripes of clouds, gap and then stripe of cloud and the gap and the stripe. Those are atmospheric gravity waves. Basically, some cloud which is slightly over dense, it will try to come down, and the less dense try to rise up. That perturbation propagates as a wave. Similarly, inside the sun also, this internal gravity waves can propagate. Okay, as I showed in one of those pictures earlier, these internal gravity waves live deep inside the sun. Okay, because the outer 30% is convecting. For example, in this picture, I have shown the depiction of the wave paths for these waves. P is the acoustic waves, and G is the internal gravity waves. As you can see, these internal gravity waves are trapped inside the base of the convective zone. So the reason is that in the convective zone, as I told you, that the temperature gradient is larger than the certain gradient, adiabatic gradient. Okay, so that makes the plasma to move. So when the plasma itself moves in bulk, then this gravity waves frequency becomes negative. Okay, so what that means is that they are trapped inside that layer. So the internal gravity waves. So there have been a lot of attempts to detect them. So even though they are trapped inside, and these are again typically very long period, as you can see in that theoretical picture. The frequencies of this in microhertz, these are of the order of peaks around 100 to a few hundred microhertz. So these are periods of several months. Okay, very low frequency or long period waves which are trapped inside the sun. And even though they are trapped inside, one expects that their evanescent tail may come up to the surface. There have been serious attempts to measure them at the surface. So far, no success because their amplitudes are very, very small. Okay, so these are the difference between the P modes and the G modes. I hope I answered the question. So the P modes are the pressure modes, just like acoustic wave. Okay, the way I speak, I produce an acoustic perturbation and you hear it. Similarly, in the sun, these pressure perturbations propagate as a P mode and they get trapped inside the sun. Okay, any other question?
Yeah, I think we're mostly done.
Okay, do we have time still?
No, I think we are running a little short, but it's okay. We'll have lunch break, I think, after this.
Okay, fine. So some of this examples and some of those slides which I missed, we will come back to it in the tutorial session. Okay. All right. Okay. I didn't go through the chat. I will try to note these questions and try to answer if it is possible.
Sure. Yeah.
All right. Okay.
Okay. So we are meeting at 2:20, 2:30.
So what is next?
So we are breaking for lunch and we'll come back at 2:30 in the afternoon.
Fine. So 2:30 is Piyali Chatterjee's lecture and the tutorial is at 4.
The tutorial starts around 4:10.
Okay.
Yeah. Okay. So thank you everyone again for joining.
Okay. Thank you.
So Crispin, are you going to leave this on?
Or what you suggest? I think let it be on. No?
Let it be on, yeah.
But YouTube, I'll close it. And the next session, I will create another link, YouTube link.
All right.
Yeah. Okay, I'll be available for a few more minutes. If anybody wants to ask any question, you can unmute and ask.
Yeah. It's not possible to read because there are so many thank you, sirs.
Yes.
Yeah. Anybody has any question, please unmute and ask. Anything about the sun? Okay. So normally we have these Kodaikanal schools which we meet in person. We have a lot of opportunities to meet and discuss. But this time